Most software developers interact with predictive algorithms every single day, yet surprisingly few understand the mathematical machinery and structural trade-offs running beneath the surface of classical linear regression. At first glance, fitting a line through data points appears to be an elementary statistical task that any modern computational library solves in a fraction of a millisecond. At its core, linear regression is a parametric supervised learning technique designed to model the quantitative relationship between a target variable, often called the response or dependent variable, and one or more input features, known as predictors or independent variables. The fundamental philosophy of parametric learning is that we assume a specific functional form for the relationship between inputs and outputs. In simple linear regression, where we work with a single predictor, we assert that the response variable is a linear function of the input feature, perturbed by an unobserved random noise term. This relationship is represented mathematically by a population regression line, which represents the true, theoretical data-generating process operating across an entire universe of observations. In real-world engineering, we almost never have access to the true population parameters. Instead, we operate on a finite sample of observed data points gathered from database records, system logs, or sensor streams. Our objective is to construct a sample regression line that estimates the true population parameters as accurately as possible. To do this, we express the estimated output as the sum of two parameters: an intercept term, which represents the expected value of the response variable when the predictor feature is equal to 0, and a slope coefficient, which quantifies the expected change in the response variable for every 1 unit increase in the predictor. To determine the optimal values for the intercept and slope coefficients, we must define a mathematical criterion that evaluates how well candidate parameter values fit our observed data. The standard technique for parameter estimation in classical regression is ordinary least squares, commonly referred to as OLS. The philosophy of ordinary least squares is centered on minimizing the discrepancy between observed target values and the predictions generated by our model. For each data point in our training set, the difference between the actual target value and the model's predicted value is called the residual. A residual represents the vertical distance between an observed data point and the estimated regression line. If we simply added together all raw residual values across a dataset, positive and negative residuals would cancel each other out, creating the false illusion of a perfect fit even for wildly inaccurate models. To prevent this cancellation, ordinary least squares calculates the square of every individual residual before summing them together, producing a metric known as the residual sum of squares, or RSS. Squaring the residuals accomplishes two vital objectives. First, it ensures that all discrepancy values are strictly non-negative, and second, it penalizes larger prediction errors disproportionately more than smaller errors. The objective function of ordinary least squares is therefore defined as minimizing the residual sum of squares across all training observations. Dividing the residual sum of squares by the total number of data points gives us the mean squared error, or MSE. Minimizing the mean squared error is mathematically equivalent to minimizing the residual sum of squares because the sample size is a constant scaling factor. To find the minimum of the error surface, we take the partial derivative of the residual sum of squares with respect to the intercept and set it to 0. Doing so reveals that the optimal intercept coefficient must equal the sample mean of the target variable minus the product of the estimated slope coefficient and the sample mean of the predictor feature. This structural property guarantees that the sample regression line always passes through the geometric center of gravity of the training data, defined by the coordinates of the sample feature mean and target mean. Next, we take the partial derivative of the residual sum of squares with respect to the slope coefficient and set it to 0. Solving this equation yields the optimal slope parameter, which can be intuitively understood as the sample covariance between the predictor feature and the target variable, divided by the sample variance of the predictor feature. This ratio reveals a clear physical mental model. The slope measures how strongly the feature and target move together relative to how much the feature varies on its own. If the predictor feature has 0 variance, meaning it is constant across all observations, the denominator becomes 0, reflecting the intuitive reality that a constant feature provides no information with which to model variations in the target. From a linear algebra perspective, ordinary least squares possesses a beautiful geometric interpretation. Imagine high-dimensional vector space where each observed data point represents a dimension. The target variable is a vector in this high-dimensional space. The predictor features form columns of a matrix, known as the design matrix, which spans a linear subspace. The predictions generated by linear regression are constrained to lie entirely within this subspace spanned by the feature columns. Ordinary least squares finds the point within the feature subspace that is closest in Euclidean distance to the actual target vector. Geometrically, the vector of residuals, the difference between the target vector and the prediction vector, is orthogonal to the entire feature subspace. This orthogonality condition is the fundamental reason why OLS projection minimizes Euclidean distance and, consequently, mean squared error. The statistical supremacy of ordinary least squares under ideal conditions is formalized by the famous Gauss-Markov theorem. This theorem establishes that, among the class of all linear unbiased estimators, the ordinary least squares estimator has the minimum variance. In engineering terms, OLS is the best linear unbiased estimator, often abbreviated as BLUE. Being unbiased means that if we were to collect infinitely many random samples from the same population and fit an OLS model to each, the average of our estimated parameters across all samples would exactly equal the true population parameters. Having minimum variance means that OLS parameter estimates fluctuate less from sample to sample than parameter estimates produced by any competing linear unbiased estimation technique. However, the guarantees of the Gauss-Markov theorem and the statistical validity of classical linear regression depend strictly on 5 foundational assumptions regarding the underlying data-generating process. Understanding these assumptions is essential for any staff engineer, as violating them can lead to unreliable predictions, invalid statistical inferences, and silent system failures in production. The first assumption is linearity in parameters. This assumption requires that the functional relationship between the target variable and the parameters is linear. Notice that this does not mean the input features themselves must be strictly linear. Rather, the coefficients multiplying those features must enter the equation linearly. We can freely transform features using logarithms, exponentials, or polynomial terms while remaining strictly within the domain of linear regression, provided the model remains a linear combination of its coefficients. The second assumption is homoscedasticity, which means constant variance of the error terms across all levels of the predictor features. Imagine evaluating system response latency against concurrent request volume. If the variance of latency measurements remains small at low request volumes but explodes into massive variability at high request volumes, the data exhibits heteroscedasticity, or non-constant error variance. While heteroscedasticity does not introduce bias into OLS parameter estimates, it invalidates the standard error calculations, rendering confidence intervals and hypothesis tests fundamentally untrustworthy. The third assumption is independence of errors, which requires that the residual associated with one observation is completely uncorrelated with the residual of any other observation. This assumption is frequently violated in time series data, spatial telemetry, or sequential logging systems where consecutive measurements exhibit positive autocorrelation. If error terms are positively correlated, OLS severely underestimates the true standard errors of the coefficients, leading engineers to incorrectly conclude that certain features are highly statistically significant when they are merely tracking sequential trends. The fourth assumption is normality of residuals. This assumption states that the random noise terms are normally distributed with a mean of 0 and a constant variance. While normality is not required for OLS parameter estimates to be unbiased, it is crucial for conducting valid hypothesis testing, calculating p-values, and constructing exact prediction intervals around model outputs. Particularly, the fifth assumption is the absence of perfect multicollinearity and the existence of sufficient feature variance. In simple linear regression, this means the predictor feature cannot be constant. In matrix terms, the design matrix containing our features must have full column rank, ensuring that no predictor can be expressed as a perfect linear combination of other predictors. If two features are perfectly correlated, the feature matrix becomes singular, rendering matrix inversion mathematically impossible. To scale linear regression from a single predictor to arbitrary feature sets, we express the system using matrix operations. Let the target values be represented by a vector of length n, where n is the number of observations. Let the features be organized into a design matrix of dimensions n rows by p columns, where p is the number of features plus an added column of ones to accommodate the intercept parameter. The vector of unknown regression weights has length p. The matrix representation of linear regression is written as y equals x times beta plus epsilon, where epsilon is the vector of unobserved random errors. Using vector calculus, the residual sum of squares can be rewritten in matrix form as the transpose of the difference vector y minus x beta multiplied by y minus x beta. Expanding this matrix expression and setting the gradient vector with respect to beta to 0 yields the celebrated normal equation. The matrix product of x transpose and x, multiplied by the parameter vector beta, equals x transpose times y. If the square matrix produced by x transpose times x is non-singular and invertible, we can multiply both sides of the normal equation by its inverse, yielding the explicit closed-form solution for the parameter estimates. Beta hat equals the inverse of x transpose x, multiplied by x transpose y. This equation represents the absolute mathematical backbone of linear regression implementation. From a computational complexity standpoint, evaluating the closed-form normal equation requires distinct mathematical phases. First, computing the matrix product x transpose x takes operational time proportional to n times p squared, where n is the number of observations and p is the number of features. Second, inverting the resulting p by p matrix using standard numerical methods like Gaussian elimination or LU decomposition requires computational complexity proportional to p cubed. Finally, multiplying the inverted matrix by x transpose y requires operations on the order of n times p plus p squared. When the feature count p is modest, say a few hundred features, computing the exact closed-form solution is blazingly fast and numerically exact. However, as the feature dimensionality grows into thousands or millions of variables, the cubic computational complexity of matrix inversion becomes an insurmountable bottleneck. Furthermore, storing the n by p design matrix in memory can exhaust RAM capacity when dealing with massive distributed datasets containing billions of rows. To overcome the memory and computational bounds of direct matrix inversion, modern production systems utilize iterative optimization algorithms, most notably gradient descent. Rather than attempting to compute the optimal weight vector, the core intuition behind gradient descent can be visualized as walking down a foggy mountain landscape toward the lowest point in a valley. At your current standing position, you feel the slope of the terrain beneath your feet. The gradient vector points in the direction of steepest ascent, the direction where the error increases most rapidly. To reduce the prediction error, you take a step in the exact opposite direction of the gradient vector. Mathematically, the gradient of the mean squared error with respect to the weight vector is calculated as -2 divided by n, multiplied by x transpose times the residual vector y minus x beta. In batch gradient descent, every single update step computes this gradient across the entire training dataset of n observations. The weight update rule calculates the new weight vector by taking the current weight vector and subtracting the learning rate multiplied by the gradient. The learning rate is a critical parameter that dictates the size of the step taken during each iteration. Selecting an appropriate learning rate is a fundamental balancing act in algorithm engineering. If the learning rate is set too small, the weight updates progress at an agonizingly sluggish pace, requiring thousands of unnecessary iterations and wasting vast computational resources. Conversely, if the learning rate is set too large, the algorithm takes oversized steps that overshoot the minimum of the loss surface. In severe cases, large learning rates cause the optimization trajectory to oscillate wildly out of control, causing the loss function to diverge to infinity. When optimizing ordinary least squares using gradient descent, we benefit from a major structural advantage. The mean squared error loss function for linear regression is strictly convex. A convex loss function forms a smooth, bowl-shaped parabolic surface in high-dimensional space with guaranteed absence of local minima. Any local minimum on a convex surface is guaranteed to be the global minimum. This property eliminates the danger of getting trapped in suboptimal local dips, ensuring that properly configured gradient descent will consistently converge toward the unique optimal parameter values. To handle streaming data feeds or datasets too large to fit into memory, engineers replace batch gradient descent with stochastic gradient descent, often abbreviated as SGD, or mini-batch gradient descent. In stochastic gradient descent, instead of calculating the exact gradient across all n observations before making a single weight update, the algorithm randomly selects a single data point, calculates the gradient based solely on that individual observation, and updates the weights immediately. This micro-update strategy drastically reduces the computational cost per iteration from order n times p down to order p. However, because a single data point contains noisy random variation, the trajectory of regardless of whether an engineer uses direct matrix inversion or iterative gradient descent, evaluating the predictive quality and statistical health of a fitted linear regression model requires rigorous diagnostic metrics. The most common metric for assessing overall fit is the coefficient of determination, denoted as R-squared. R-squared quantifies the proportion of total variance in the target variable that is explained by the linear model. It is computed as 1 minus the ratio of the residual sum of squares to the total sum of squares, where total sum of squares, while R-squared provides an intuitive percentage scale, it possesses a dangerous fundamental flaw. Adding more predictor features to a linear regression model will almost always increase the R-squared value, or at worst leave it unchanged, even if the newly added features contain complete random noise. This occurs because the OLS optimization algorithm will always find some tiny non-zero coefficient that uses the random noise to marginally reduce residual error on the training set. To guard against false confidence created by feature bloat, engineers use adjusted R-squared. Adjusted R-squared introduces an explicit penalty for feature complexity. It modifies the standard R-squared calculation by dividing the residual sum of squares by its degrees of freedom, n minus p minus 1, and dividing the total sum of squares by its degrees of freedom, n minus 1. If you add a new feature that does not improve the model fit by an amount greater than what would be expected by random chance, the adjusted R-squared value will decrease, signaling that the added feature adds unnecessary complexity without meaningful predictive power. Alongside R-squared metrics, model accuracy is evaluated using root mean squared error, or RMSE, and mean absolute error, or MAE. RMSE measures the square root of the average squared residual, expressing the prediction error in the exact same physical units as the original target variable. Because RMSE squares errors before averaging, it places heavy emphasis on large errors, making it an excellent metric when large mispredictions are disproportionately harmful to system operations. Mean absolute error computes the average of the absolute residual values, offering a robust measure of typical error that is less sensitive to extreme outliers than RMSE. To verify that a deployed linear regression model maintains structural integrity, staff engineers conduct thorough residual diagnostics. Plotting fitted values against raw residuals allows engineers to visually detect violations of model assumptions. If the residual plot exhibits a random, uniform cloud of points scattered evenly around zero, the assumptions of linearity and homoscedasticity are satisfied. However, if the residuals display a distinct curved pattern, it indicates that the underlying relationship is nonlinear, signaling that the engineer should incorporate polynomial terms or nonlinear feature transformations. If the spread of residuals expands or contracts systematically as fitted values increase, forming a characteristic megaphone shape, the model suffers from heteroscedasticity. To formally test for heteroscedasticity without relying on visual interpretation alone, engineers run statistical tests such as the Brush-Pagan test or White's test. When heteroscedasticity is present, engineers can apply variance-stabilizing transformations to the target variable, such as logarithmic transformations, or transition from ordinary least squares to weighted least squares, where observations with higher error variance are assigned lower weight in the objective function. Finally, residual analysis must inspect for influential observations and leverage points that disproportionately distort the fitted regression line. Leverage measures how far an observation's predictor feature values deviate from the mean of those features across the dataset. Observations with extreme feature values possess high leverage, meaning they have the structural potential to single-handedly swing the regression line toward themselves. If a high leverage point also has a large residual value, it becomes an influential observation that fundamentally alters the estimated slope and intercept parameters. To quantify the overall influence of each data point, engineers calculate Cook's distance. Cook's distance measures the aggregate shift in all fitted model predictions that occurs when a specific single observation is deleted from the training dataset. Observations exhibiting a Cook's distance significantly greater than 1 indicate highly influential data points that warrant deep investigation, as they may represent data corruption, sensor malfunction, or distinct operational regimes that require dedicated submodels. In summary, classical linear regression represents far more than a simple line-fitting exercise. From its formulation as an ordinary least squares optimization problem to its geometric representation as an orthogonal projection in high-dimensional vector space, linear regression provides a rigorous framework for quantitative modeling. While single-variable linear regression provides a foundational understanding of slope and intercept optimization, real-world engineering systems rarely operate in isolation. System performance, financial valuation, latency forecasting, and user engagement are governed by complex webs of interconnected signals. To capture these multidimensional dynamics, we expand our mathematical framework from simple linear regression to multiple linear regression. Transitioning to multiple linear regression moves us from fitting a two-dimensional line on a flat plane to fitting a hyperplane within a high-dimensional vector space. In multiple linear regression, the response variable is modeled as a linear combination of p distinct predictor variables, each weighted by its own specific regression coefficient, plus an overall intercept term and an unobserved random error. The interpretation of regression coefficients undergoes a fundamental conceptual shift when moving from simple to multiple linear regression. In a simple model with one predictor, the slope coefficient reflects the total observed relationship between the feature and the target, absorbing all indirect influences from unmeasured variables. In multiple linear regression, each individual coefficient represents a partial regression coefficient. This concept of ceteris paribus, holding all other features constant, is of paramount importance for engineering decision-making. Imagine modeling application response latency based on two input features: incoming request throughput and memory utilization. If you fit two separate single-variable regression models, request throughput and memory utilization might both appear to have massive positive slopes because high request throughput causes memory usage to rise. However, fitting a multiple linear regression model containing both features simultaneously isolates their unique independent contributions. The partial coefficient for request throughput tells you how much latency increases when request throughput rises while memory utilization remains perfectly unchanged. This isolation of partial effects allows engineers to disentangle confounding variables and identify the true underlying drivers of system behavior. However, interpreting partial regression coefficients becomes severely compromised when input features are highly correlated with one another. This phenomenon is known as multicollinearity. Multicollinearity occurs when two or more predictor variables in a regression model share a strong linear relationship, making it difficult for the ordinary least squares algorithm to isolate their independent partial effects. To build a physical mental model of multicollinearity, visualize trying to determine the individual weights of two people standing together on a single balance scale. Geometrically, near-perfect multicollinearity causes the square matrix product X transpose X to become ill-conditioned, bringing its matrix determinant close to zero. When a matrix is near singular, computing its inverse yields extremely large numerical values. Consequently, the sampling variance of the estimated regression coefficients explodes. While the overall model may still achieve a high R-squared and accurate total predictions, the individual partial regression coefficients become highly volatile. Tiny perturbations in the training data can cause a coefficient to flip dramatically from a large positive value to a large negative value, destroying the interpretability of the model and causing severe instability during hypothesis testing. To detect and quantify the severity of multicollinearity within a feature set, engineers rely on the variance inflation factor, commonly abbreviated as VIF. The variance inflation factor measures how much the variance of an estimated regression coefficient is inflated due to collinearity with other predictors in the model. To calculate the VIF for a specific feature J, we fit an auxiliary linear regression model where feature J acts as the target variable and all remaining p-1 features serve as predictors. We calculate the coefficient of determination R² sub J from this auxiliary regression. The variance inflation factor for feature j is defined mathematically as 1 divided by the quantity 1 minus r squared sub j. If feature j is completely uncorrelated with all other features, the auxiliary r squared sub j is 0, resulting in a VIF of 1, which indicates zero variance inflation. As the auxiliary r squared sub j approaches 1, meaning feature j can be almost perfectly predicted by a linear combination of the remaining features, the denominator approaches 0 and the VIF shoots up toward infinity. In practical engineering pipelines, a variance inflation factor value of 1 indicates complete absence of collinearity. VIF values between 1 and 5 suggest moderate correlation that is typically manageable. However, VIF values exceeding 5 or 10 signal severe multicollinearity that demands remedial action. When severe multicollinearity is detected, staff engineers deploy several corrective strategies. Dropping one of the redundant collinear features, combining correlated features into a single composite index, applying principal component analysis to project features onto orthogonal axes, or introducing regularization penalties such as ridge regression. Evaluating the statistical validity of a multiple linear regression model requires a structured hierarchical hypothesis testing framework. When analyzing a model with P features, the first question we must answer is not whether any individual feature is important, but whether the entire collection of features possesses any collective predictive power whatsoever. This is evaluated using the global F-test. The null hypothesis of the global F-test asserts that all P partial regression coefficients are simultaneously equal to 0, meaning that none of the features have any true linear relationship with the target variable. The alternative hypothesis states that at least one coefficient is non-zero. The F-statistic is calculated as the ratio of the explained mean square to the residual mean square. The explained mean square represents the regression sum of squares divided by p degrees of freedom, while the residual mean square represents the residual sum of squares divided by n minus p minus 1 degrees of freedom. A naive developer might wonder why we need a global F-test when we could simply perform individual t-tests on each of the p coefficients. The reason is the mathematical problem of multiple testing and family-wise error rate expansion. If you conduct 20 independent hypothesis tests, each at a standard 5% significance level, the probability of obtaining at least one false positive result purely by random chance rises to over 64%. Inspecting 20 individual t-tests without a global test creates a massive risk of declaring for each individual predictor. The t-statistic is computed by taking the estimated partial coefficient and dividing it by its standard error. Under the null hypothesis that the true coefficient is 0, this ratio follows a student's t-distribution with n minus p minus 1 degrees of freedom. A large absolute t-statistic, corresponding to a p-value below a chosen threshold such as 0.05 or 0.01, provides strong statistical evidence that the feature contributes unique predictive value to the model after accounting for all other included variables. Before feeding features into a multiple linear regression model, engineers must carefully consider feature scaling and standardization. In real-world applications, raw features arrive in wildly different physical units and numerical scales. For instance, memory capacity measured in gigabytes ranging from 1 to 256, alongside CPU utilization measured as a ratio between 0 and 1. If raw unscaled features are fed directly into ordinary least squares computed via gradient descent, the vast difference in feature scales distorts the geometry of the loss surface. Features with massive numerical scales produce extremely steep loss gradients, while features with tiny numerical scales produce nearly flat loss gradients. This turns the convex loss landscape into a deeply stretched, elongated elliptical canyon. Gradient descent optimization struggles in such environments, bouncing back and forth wildly across the steep canyon walls while making agonizingly slow progress along the valley floor toward the true minimum. To solve this convergence bottleneck, engineers apply z-score standardization, also known as standard scaling. Standard scaling transforms each feature by subtracting its sample mean and dividing by its sample standard deviation. This rescales every feature to have a mean of exactly 0 and a standard deviation of 1. Standardizing the features transforms the stretched elliptical loss landscape into a perfectly symmetric, circular bowl. In this balanced geometry, the gradient vector points directly toward the global minimum, allowing gradient descent to converge rapidly with stable step sizes. Beyond optimization benefits, feature standardization fundamentally enhances model interpretability. When features remain in their raw physical units, the magnitude of a regression coefficient depends entirely on the scale of its underlying variable. A feature measured in tiny units will naturally have a tiny coefficient, even if it is the most critically important predictor in the system. By contrast, when all features are standardized, the resulting coefficients, often called beta weights, are directly comparable on an equal scale. An engineer can inspect the absolute values of standardized beta weights to instantly rank the relative structural influence of each predictor across the entire system. Standard multiple linear regression assumes an additive model architecture, meaning that the effect of a change in feature 1 on the target variable is entirely independent of the current value of feature 2. However, real-world engineering phenomena are frequently non-additive, exhibiting rich synergy or interaction effects. And to capture this non-additive synergy within a linear model, engineers create explicit interaction terms by taking the mathematical product of the two interacting features and adding it as a new predictor column in the design matrix. The model equation then includes an intercept, main effect terms for feature 1 and feature 2, and an interaction term weighted by its own interaction coefficient. The partial derivative of the target with respect to feature 1 in an interaction model reveals that the effective slope multiplying feature 1 is no longer a constant value. Instead, it is equal to the main coefficient of feature 1 plus the interaction coefficient multiplied by feature 2. This elegant formulation allows linear regression to model dynamic, conditional relationships while remaining strictly linear in its parameters. When incorporating interaction terms into a regression architecture, staff engineers strictly follow the main effects principle. The main effects principle dictates that if an interaction term between two features is included in a model, the individual main effect terms for both constituent features must also be retained in the model, even if their individual t-statistic p-values appear statistically insignificant. Dropping a main effect term while retaining its interaction term artificially forces the interaction model to pass through 0 along that feature axis, distorting the parameter estimates and corrupting the geometric interpretation of the fitted surface. In addition to continuous numerical measurements, real-world feature pipelines frequently contain qualitative categorical variables, such as server cloud provider, storage disk type, or deployment environment tier. Because linear regression relies on mathematical matrix operations, categorical strings cannot be processed directly. Engineers must convert discrete categories into quantitative numerical representations through dummy coding, also known as one-hot encoding. For a binary categorical variable with two possible states, such as storage type being either solid-state drive or traditional spinning disk, we construct a single indicator variable or dummy variable. This dummy variable takes a value of 1 if the storage type is solid-state drive, and a value of 0 if it is a spinning disk. When this binary dummy feature is included in a linear regression model, its estimated coefficient represents the expected difference in the target variable between solid-state drives and traditional spinning disks, holding all other features constant. The baseline category where the dummy variable equals 0 is absorbed entirely into the model's intercept term. When dealing with a categorical variable that has k distinct categories, for example, cloud region spanning 4 distinct geographic locations, engineers must construct exactly k-1 dummy variables. One category is intentionally chosen as the reference baseline and receives no dedicated dummy column. If a developer mistakenly creates k-dummy variables for a k-category feature while retaining the model intercept, they trigger a catastrophic structural failure known as the dummy variable trap. The dummy variable trap is a classic form of perfect multicollinearity. Because every observation must belong to exactly one of the k categories, the sum of all k dummy columns for any given row will equal exactly 1. If the model matrix also contains a constant column of 1s for the intercept, the kth dummy column can be expressed as a perfect linear combination of the intercept column minus the sum of the other k-1 dummy columns. This linear dependency renders the design matrix X transpose X singular and non-invertible, causing the mathematical solver to crash or produce nonsense coefficients. Leaving out one reference category avoids the trap completely, ensuring full column rank while allowing all dummy coefficients to be interpreted cleanly as differential shifts relative to the reference baseline. As feature pipelines grow to encompass hundreds of candidate variables, engineers face the challenge of model selection and capacity control. Including irrelevant or noisy features degrades prediction variance, increases computational latency, and risks overfitting. To select optimal feature subsets, classical statistics provides automated iterative search procedures, forward selection, backward elimination, and stepwise regression. Forward selection begins with an empty model containing only an intercept, and iteratively adds the single feature that produces the largest statistically significant reduction in residual error at each step, stopping when no remaining feature meets the entry threshold. Backward elimination starts with a fully saturated model containing all candidate features, and sequentially removes the feature with the least statistically significant t-statistic until all remaining features satisfy the retention threshold. Stepwise regression combines both approaches, evaluating at each iteration whether previously added features should be removed after new features enter the model. To compare competing feature subsets of varying size, engineers use information criteria penalties such as Aikaika Information Criterion, or AIC, and Bayesian Information Criterion, or BIC. Both AIC and BIC evaluate model quality by balancing goodness of fit against a strict mathematical penalty for the total number of estimated parameters. BIC imposes a larger penalty for model complexity than AIC as sample size grows, making BIC favor leaner, more parsimonious model architectures. In conclusion, multiple linear regression extends linear modeling into complex, multivariable engineering domains. By mastering partial coefficient interpretation, detecting and mitigating multicollinearity via VIF, conducting global F-tests, standardizing features to balance optimization landscapes, capturing non-additive synergies with interaction terms, avoiding the dummy variable trap, and applying principled feature selection, software engineers can construct highly interpretable and robust multivariable models for production systems. When faced with nonlinear relationships, forcing a straight line or flat hyperplane through the data leads to severe underfitting. Underfitting occurs when a model lacks the capacity to capture the underlying geometric curvature of the true data-generating process, resulting in high systematic bias. To model nonlinear phenomena without abandoning the powerful optimization machinery of linear models, engineers employ the concept of basis expansion. Basis expansion is a fundamental transformation strategy where original input features are mapped into a higher dimensional space using nonlinear transformation functions. Instead of fitting a model directly on the raw feature X, we fit a linear model on a collection of derived features such as x squared, x cubed, or logarithmic transformations of x. Because the model equation remains a linear combination of its unknown regression coefficients, we can continue to use ordinary least squares, normal equations, and gradient descent while capturing intricate nonlinear shapes. The most intuitive form of basis expansion is polynomial regression. In polynomial regression, we extend a single predictor variable x by adding raised power terms up to a specified degree d. The resulting model equation expresses the target response as the intercept plus coefficient 1 times x plus coefficient 2 times x squared, continuing up to coefficient d times x to the power of d. Adding polynomial terms allows the regression line to bend and curve, fitting parabolic arcs with quadratic terms, S-shaped curves with cubic terms, and multi-peak waves with higher degree terms. To understand how polynomial regression operates, visualize taking a one-dimensional feature axis, such as request concurrency, and bending it into a higher dimensional space. The parabolic quadratic term measures the acceleration or deceleration of the target response, capturing rate of change dynamics that a flat slope cannot represent. However, increasing the polynomial degree d introduces significant engineering trade-offs and structural vulnerabilities. As the polynomial degree rises, the model gains extreme geometric flexibility, allowing it to pass through increasingly complex data arrangements. But this flexibility comes at a severe cost: high variance and extreme sensitivity to training noise. A major numerical flaw of raw monomial basis representations, such as x, x squared, x cubed, is extreme numerical instability caused by the conditioning of the Vandermonde matrix. When creating higher powers of continuous features, columns of x and x squared become intensely correlated, creating severe multicollinearity within the design matrix. As the degree d increases beyond 4 or 5, the matrix product x transpose x becomes exponentially ill-conditioned. Numerical floating point rounding errors in CPU registers begin to corrupt matrix inversion calculations, causing solved parameters to lose floating point precision. To fix this numerical conditioning bottleneck without abandoning polynomial models, numerical software implementations utilize orthogonal polynomials, such as Chebyshev or Legendre polynomials. Orthogonal polynomials transform raw power features into mutually orthogonal basis functions. By guaranteeing that every polynomial feature column is strictly uncorrelated with all other degree columns, orthogonal polynomials stabilize matrix inversion, eliminate numerical precision degradation, and allow individual polynomial coefficients to be evaluated independently without affecting lower degree parameter estimates. Despite orthogonal transformations, global polynomial regression still suffers from a classic mathematical instability known as Runge's phenomenon. Runge's phenomenon refers to severe wild oscillations that appear near the boundaries of the training feature domain when fitting high-order polynomials over equally spaced data points. While a high-degree polynomial may fit points in the middle of the feature domain reasonably well, it frequently swings out of control near the edges, projecting absurdly large positive or negative predictions for inputs slightly outside the central range. Furthermore, polynomial regression suffers from a catastrophic curse of dimensionality when extended to multivariable datasets. If a dataset contains p features and an engineer wishes to include all polynomial terms up to degree d, including all cross-product interaction terms, the total number of generated features expands combinatorially as p plus d choose d. For instance, a modest feature set of 20 predictors transformed to a degree 4 polynomial explodes into over 10,000 feature columns. To overcome the global instability of high-degree polynomials, staff engineers transition from global transformations to localized, piecewise modeling strategies. The foundational stepping stone of piecewise modeling is piecewise polynomial regression. Instead of fitting a single high-degree polynomial across the entire domain of a feature, piecewise polynomial regression partitions the feature domain into multiple distinct subintervals separated by numerical boundary thresholds called knots. Within each subinterval, a separate low-degree polynomial, typically a cubic polynomial of degree 3, is fitted independently. Because each local polynomial is restricted to a small range of the feature space, it can adapt to local curvature without causing wild oscillations in distant regions of the dataset. However, fitting completely independent polynomials across adjacent subintervals creates a severe structural defect. Visible, unnatural step discontinuities and sharp angular breaks at the knot boundaries. To produce a smooth, physically realistic curve across the entire feature space, we must enforce mathematical continuity constraints at every knot. First, we enforce value continuity, requiring that the polynomials fitting the left and right sides of a knot meet at the exact same vertical coordinate. A piecewise cubic polynomial that satisfies value continuity, first derivative continuity, and second derivative continuity at every internal knot is defined as a cubic spline. Cubic splines represent the gold standard of nonlinear curve fitting. By using cubic terms, they possess enough flexibility to capture complex local smooth curvature, while second derivative continuity guarantees that the resulting fitted curve appears completely seamless and visually smooth across all knot boundaries. To construct a cubic spline mathematically, engineers utilize a truncated power basis representation or B-spline basis. For a cubic spline with k knots, the truncated power basis set consists of the original feature x, x squared, x cubed, and k additional truncated power terms. A truncated power term for a knot value is defined as the cube of the quantity x minus the knot value if x is greater than the knot value, and 0 otherwise. When x crosses a knot threshold, the corresponding truncated power term activates smoothly, allowing the curve to adjust its trajectory without violating derivative continuity. Despite their power, standard cubic splines still exhibit high prediction variance in the boundary regions beyond the smallest and largest knots, where the curve relies on unconstrained cubic extrapolation. To eliminate this edge instability, engineers utilize natural cubic splines. A natural cubic spline is a specialized cubic spline that enforces an additional boundary constraint. The function must be strictly linear in the regions outside the boundary knots. By forcing the function to revert to a simple straight line in the extreme tail regions where data is sparse, selecting the optimal number and placement of knots is a crucial hyperparameter decision in spline modeling. Engineers can place knots uniformly across the feature range, or place them at specific empirical quantiles of the feature distribution, such as 25th, 50th, and 75th percentiles, ensuring that dense data regions receive more knots than sparse tail regions. Placing knots densely in regions where the data exhibits rapid nonlinear shifts allows the spline to capture intricate behavior, while placing knots sparsely in stable regions prevents overfitting. To automate knot selection completely without manually inspecting feature plots or hard-coding quantile boundaries, engineers turn to smoothing splines. A smoothing spline eliminates the need to select explicit knot locations by placing a potential knot at every single unique training data point. To prevent this vast collection of knots from perfectly interpolating the noise in the training set, smoothing splines modify the objective function by introducing an explicit roughness penalty. The smoothing spline objective function minimizes the residual sum of squares plus a regularization penalty parameter, lambda, multiplied by the integrated squared second derivative of the function across its entire domain. The second derivative of a function measures its curvature or roughness. A straight line has a second derivative of 0, representing 0 roughness. A wildly oscillating curve has massive second derivative values, representing high roughness. The hyperparameter lambda acts as a precise dial controlling the trade-off between training fit and curve smoothness. If lambda is set to 0, the roughness penalty is completely turned off, and the smoothing spline becomes an unconstrained interpolating function that wiggles violently to touch every training point. If lambda approaches infinity, the penalty against curvature becomes infinitely severe, forcing the second derivative to 0 everywhere and collapsing the smoothing spline into a standard ordinary least squares linear regression line. To efficiently select the optimal smoothing parameter lambda without running completely expensive k-fold cross-validation repeatedly, engineers utilize generalized cross-validation, or GCV. Generalized cross-validation computes an analytical approximation of leave one out cross-validation error in a single computational pass by leveraging the trace of the hat projection matrix. This computational shortcut allows smoothing splines to tune their effective degrees of freedom in milliseconds, making them extremely practical for large-scale data pipelines. An alternative non-parametric approach to nonlinear modeling is local regression, frequently referred to as LUS or LOIS, which stands for locally weighted scatterplot smoothing. Unlike polynomial regression or splines, which construct a single global mathematical formula, LUS is a memory-based, lazy learning algorithm that fits localized linear models on the fly for specific query points. To compute a prediction at a target query point x sub 0 using LOESS, the algorithm performs a sequence of localized computations. First, it identifies the fraction span of training data points that are closest in Euclidean distance to the query point x sub 0. Second, it assigns a scalar weight to each neighboring training point using a smooth kernel weighting function, such as the tricube kernel. Training points located extremely close to x sub 0 receive large weights, while points farther away receive smaller weights, decaying smoothly to 0 at the boundary of the neighborhood span. Third, LUS fits a weighted linear or quadratic regression model using only these local training points, minimizing the locally weighted residual sum of squares. Fourth, the fitted local model generates a prediction specifically for the query point x sub 0. Once the prediction is delivered, the temporary local model is discarded. To predict at a different query point, the entire localized weighting and fitting procedure is repeated from scratch. LUS provides extraordinary flexibility because it makes zero global assumptions about the functional form of the data-generating process. It can adapt seamlessly to arbitrary complex shapes, localized sharp bends, and varying density regions. However, LUS comes with a severe production engineering drawback: extreme computational latency during inference. Because LOESS does not collapse training data into a compact parameter weight vector, it must retain the entire training dataset in memory during deployment. Generating a single prediction requires scanning the training set to identify nearest neighbors, computing kernel distance weights, and solving a localized weighted matrix inversion problem. The computational cost per query scales linearly with training set size n, making LUS far too slow for low-latency production APIs handling thousands of concurrent real-time requests. Consequently, LUS is primarily utilized as an exploratory data analysis tool rather than a production inference engine. When engineering multivariable systems with multiple nonlinear inputs, fitting separate high-dimensional splines across all features simultaneously leads to severe computational bottlenecks and loss of interpretability. To resolve this challenge, staff engineers deploy generalized additive models, commonly abbreviated as GAMs. Generalized additive models extend multiple linear regression by replacing each linear feature term with a smooth, nonlinear function specific to that predictor. The target response in a GAM is modeled as the intercept plus function 1 of feature 1, plus function 2 of feature 2, continuing to function p of feature p, plus random error. The individual nonlinear functions can be smoothing splines, natural splines, or local regression curves. GAMs represent a masterclass in structural engineering design because they bridge the gap between flexible nonlinear modeling and human interpretability. Because the nonlinear functions are combined additively, engineers can inspect the individual partial dependence plots for each feature in isolation. You can examine the exact nonlinear curve relating CPU utilization to latency while holding memory usage and disk operations additive and constant. To capture multidimensional nonlinear interactions, such as geographical latitude and longitude coordinates in spatial models, GAMs can incorporate thin plate splines. Thin plate splines extend single variable splines into 2 or more continuous dimensions simultaneously, minimizing a multidimensional curvature penalty to form smooth nonlinear surfaces over multidimensional feature coordinates. To estimate the nonparametric component functions within a GAM, optimization algorithms utilize the backfitting algorithm. The backfitting algorithm is an iterative coordinate descent strategy that updates one feature's nonlinear function at a time while holding all other feature functions fixed. The algorithm begins by initializing all feature functions to 0 or simple linear fits. At each iteration, it isolates feature j and calculates the partial residuals, the difference between the target variable and the sum of all currently estimated functions for all other features. It then fits a nonlinear smoothing spline or LUS curve using feature j as the input and the partial residuals as the target. The updated function for feature j replaces its predecessor, and the algorithm steps to the next feature. This iterative backfitting process repeats sequentially across all features until the estimated functions converge to a stable equilibrium state. In production engineering, selecting between polynomial expansions, splines, LUS, and GAMs requires evaluating explicit operational trade-offs. Polynomial expansions are computationally lightweight during inference, requiring simple vector dot products, but suffer from Runge's phenomenon boundary instability, numerical conditioning errors, and combinatorial feature explosion. Natural cubic splines offer localized smoothness and robust linear edge extrapolation, making them the preferred choice for single variable or low-dimensional nonlinear feature engineering. GAMs provide exceptional interpretability for complex multivariable systems, allowing engineers to visualize nonlinear operational boundaries while preserving additive structure. By mastering basis expansions, orthogonal polynomials, cubic splines, smoothing spline penalties, generalized cross-validation, local regression mechanics, and generalized additive models, software engineers can equip their predictive pipelines with the geometric flexibility required to model real-world nonlinear phenomena accurately and reliably. As software data pipelines collect an ever-increasing array of telemetry signals, user behavioral tracking attributes, and high-dimensional embeddings, feature dimensions rapidly scale into hundreds or thousands of variables. In these high-dimensional regimes, classical ordinary least squares linear regression hits a fundamental operational wall. When the number of features p approaches or exceeds the number of available training observations n, the matrix X transpose X becomes singular or severely ill-conditioned. Even when observation count n is comfortably larger than feature count p, fitting an unconstrained ordinary least squares model on high-dimensional data frequently leads to catastrophic overfitting. Overfitting occurs when a model uses its unconstrained capacity to memorize random sampling noise, microfluctuations, and spurious correlations present in the training set. While the resulting model achieves near-zero error on training data, its performance degrades severely when evaluated on fresh, unseen production data. To understand why unconstrained linear regression fails in high dimensions, staff engineers analyze the system through the lens of the bias-variance trade-off. The total expected generalization error of any predictive machine learning model can be decomposed into three distinct components: squared bias, variance, and irreducible error. Bias measures the systematic error introduced by approximating a complex, high-dimensional real-world relationship with a simplified functional form. A model with high bias underfits the data, consistently missing true structural patterns regardless of how much data it observes. Variance measures the sensitivity of the model's parameter estimates to random fluctuations in the specific training dataset. A model with high variance fits its training set intensely, but its weight coefficients shift dramatically if trained on a slightly different random sample from the same data source. Unconstrained ordinary least squares is explicitly designed to be an unbiased estimator. However, to achieve zero statistical bias in high-dimensional or collinear feature spaces, OLS pays an astronomical penalty in variance. The coefficient weights explode to massive positive and negative values, canceling each other out across correlated features to fit minor noise fluctuations. Regularization is the engineering practice of introducing controlled mathematical constraints onto parameter weights to optimize the bias-variance trade-off. By imposing a penalty on parameter magnitude, regularization intentionally introduces a small, controlled amount of statistical bias into the model. In exchange for this tiny increase in bias, regularization produces a massive, dramatic reduction in parameter variance. Shrinking the parameter weights stabilizes the model, prevents parameter explosion, and significantly reduces generalization error on unseen production data. Before applying any regularization penalty, staff engineers enforce a mandatory pre-processing requirement, standardizing all predictor features to have a mean of 0 and unit variance. If features are regularized in their raw, unscaled forms, the mathematical penalty will disproportionately penalize features measured in large physical units. For instance, a memory feature measured in bytes will have tiny raw coefficient magnitudes, escaping penalty, while a feature measured in gigabytes will have large coefficient magnitudes and suffer severe penalization regardless of its predictive importance. Standardizing features ensures that the regularization penalty is applied uniformly and equitably across all predictor variables. The foundational regularization technique in classical linear modeling is ridge regression, also known as L2 regularization or Tikhonov regularization. Ridge regression modifies the ordinary least squares objective function by adding an explicit penalty proportional to the sum of the squared regression coefficients. The ridge regression objective function minimizes the residual sum of squares plus a scalar hyperparameter, lambda, multiplied by the sum of squared weights from feature 1 to feature p. Notice that the intercept term is explicitly excluded from the penalty function. We do not penalize the model for shifting its baseline vertical offset to match the target mean. The hyperparameter lambda controls the strength of the L2 penalty. If lambda is set to 0, the penalty term vanishes completely, and ridge regression reverts identically to standard unconstrained ordinary least squares. As lambda increases above 0, the penalty against large coefficient magnitudes becomes increasingly severe, forcing the optimization algorithm to shrink all regression weights continuously towards 0. If lambda approaches infinity, the penalty dominates the objective function completely, forcing all feature weights to 0 and leaving only the sample mean intercept. From a Bayesian statistical perspective, ridge regression possesses a deep intuitive interpretation. It is mathematically equivalent to maximum a posteriori, or MAP, estimation under a zero-mean Gaussian prior distribution on the regression weights. By placing a Gaussian prior centered at 0 over the parameter space, we express a probabilistic belief that feature weights are likely to be small. The regularization hyperparameter lambda reflects the inverse variance of this Gaussian prior belief. From a linear algebra standpoint, ridge regression solves the matrix singularity problem in a single mathematical step. Recall that ordinary least squares computes parameters using the inverse of x transpose x. When features are highly collinear or when p exceeds n, x transpose x is non-invertible. Ridge regression modifies the normal equation by adding lambda times the identity matrix to x transpose x before taking the inverse. The closed-form analytical solution for ridge regression is written as beta hat ridge equals the inverse of the quantity x transpose x plus lambda times I, multiplied by x transpose y, where I is the p by p identity matrix. Adding lambda times the identity matrix adds a constant positive scalar lambda to every diagonal element of x transpose x. Geometrically, this operation shifts all eigenvalues of the matrix upward by an amount equal to lambda. Because all eigenvalues are strictly positive, the matrix x transpose x plus lambda times I is guaranteed to be positive definite and non-singular, rendering matrix inversion mathematically possible and numerically stable even when p is far larger than n or when features are perfectly collinear. To build a spatial mental model of ridge regression, visualize the optimization loss landscape in two-dimensional weight space. The residual sum of squares forms elliptical contour lines centered around the unconstrained OLS minimum point. The L2 penalty forms a perfectly spherical, circular constraint boundary centered at the origin, where the distance from the origin is proportional to the sum of squared weights. Ridge regression finds the exact point where the expanding elliptical contours of the residual sum of squares touch the outer boundary of the spherical penalty constraint. Because a sphere is smooth, round, and continuous everywhere, the contact point between the elliptical loss contours and the L2 constraint sphere almost never occurs directly on the coordinate axis. Consequently, ridge regression continuously shrinks parameter weights towards 0, but never sets any coefficient to exactly 0. All p features remain active in the model, retaining a complete feature-dense representation. While this continuous weight decay effect makes ridge regression exceptional for handling dense correlated telemetry, it does not perform automated feature selection. When staff engineers require an interpretable model that automatically eliminates irrelevant features, they transition from L2 regularization to Lasso regression, which stands for Least Absolute Shrinkage and Selection Operator, also known as L1 regularization. Lasso regression modifies the ordinary least squares objective function by adding a penalty proportional to the sum of the absolute values of the regression coefficients, rather than their squared values. The Lasso objective function minimizes the residual sum of squares plus lambda multiplied by the sum of absolute values of weights from feature 1 to feature p. From a Bayesian probabilistic viewpoint, Lasso regression is mathematically equivalent to maximum a posteriori estimation under a zero-mean Laplace, or double exponential prior distribution on parameter weights. The sharp peak of the Laplace prior at 0 reflects a strong probabilistic prior belief that many feature weights in the system are identically 0. This subtle mathematical modification, changing the exponent of parameter weights from 2 to 1, fundamentally alters the geometric behavior of the optimization constraint. To understand why Lasso regression performs automatic feature selection while ridge regression does not, compare their penalty constraint geometries in two-dimensional weight space. While the L2 penalty forms a smooth, round sphere, the L1 penalty forms a diamond-shaped polytope with sharp corners positioned precisely on the coordinate axis where individual weights equal 0. When the expanding elliptical contour lines of the residual sum of squares meet the L1 diamond constraint, they are highly likely to make first contact at one of the sharp diamond corners located directly on an axis. When contact occurs at a corner, the corresponding weight parameter for that axis is driven to exactly 0. As the regularization hyperparameter lambda increases in Lasso regression, parameter weights are not merely shrunk continuously. Instead, insubstantial or redundant feature weights hit 0 one by one and are completely erased from the model equation. The resulting fitted model is sparse, retaining non-zero weights for only a small subset of the most critically predictive features. This automatic sparsity makes Lasso regression an exceptional tool for feature selection, model compression, and building parsimonious architectures in high-dimensional environments. However, the absolute value function in the L1 penalty introduces an optimization challenge. The L1 norm is non-differentiable at 0 because of the sharp corner point. Consequently, we cannot compute standard calculus partial derivatives or use simple closed-form matrix inversions to solve Lasso regression. To solve Lasso optimization efficiently, numerical implementations use subgradient calculus and coordinate descent, or path algorithms like least angle regression, abbreviated as LARS. LARS computes the entire regularization path of non-zero features in a sequence of exact geometric steps, running in the same computational order of magnitude as a single OLS fit. In coordinate descent, the algorithm updates one weight parameter at a time while holding all other p-1 weights strictly fixed. When isolating weight j in coordinate descent, the optimization problem simplifies to a single variable update using the soft thresholding operator. The soft thresholding operator evaluates the partial correlation between feature j and the residual target. If the magnitude of this partial correlation is smaller than the regularization threshold lambda, the soft thresholding operator clips the weight parameter to exactly 0. If the partial correlation exceeds lambda, the operator shrinks its value towards 0 by subtracting lambda from its magnitude while preserving its original sign. Coordinate descent sweeps repeatedly through all p features until the weight vector reaches convergence. Despite its feature selection capabilities, Lasso regression suffers from two distinct engineering limitations. First, if feature dimension p is greater than sample size n, Lasso regression can select at most n non-zero features before saturating, discarding any remaining predictive features. Second, if a dataset contains a group of highly correlated predictors, such as multiple redundant sensor feeds tracking the exact same physical metric, lasso regression tends to arbitrarily select one single feature from the correlated group and set all other correlated features to 0. This arbitrary feature drop makes lasso unstable for interpreting grouped feature dependencies. To overcome the limitations of both ridge and lasso regression, engineers deploy elastic net regularization. Elastic net combines both L1 and L2 penalty terms into a unified objective function. The elastic net objective function minimizes the residual sum of squares plus a composite penalty, lambda 1 multiplied by the sum of absolute L1 weights, plus lambda 2 multiplied by the sum of squared L2 weights. In modern machine learning frameworks, elastic net parameterizes this composite penalty using two intuitive hyperparameters: alpha, which controls the overall total penalty strength, and L1 ratio, which controls the mixing balance between L1 and L2 penalties. An L1 ratio of 1 corresponds to pure lasso regression, an L1 ratio of 0 corresponds to pure ridge regression, and intermediate values between 0 and 1 balance both penalties. Elastic net achieves a masterclass engineering compromise. The L1 penalty component drives automatic sparsity and feature selection, while the L2 penalty component enforces a grouping effect. The grouping effect ensures that when a cluster of strongly correlated features enters the model, elastic net shrinks their coefficients together and retains or removes the entire correlated group as a unit, rather than arbitrarily picking one and discarding the rest. Furthermore, elastic net easily selects more than n features when p is greater than n, making it the preferred default regularization framework for high-dimensional production pipelines. Regardless of whether an engineer chooses ridge, lasso, or elastic net, selecting the optimal regularization strength hyperparameter lambda is critical. Setting lambda too small leads to overfitting and high variance, while setting lambda too large leads to severe underfitting and high bias. To find the optimal hyperparameter value objectively, engineers implement k-fold cross-validation. In k-fold cross-validation, the training dataset is randomly partitioned into k equal-sized subsets, known as folds, typically setting k to 5 or 10. The model training and evaluation procedure runs across k sequential iterations. In each iteration, one fold is held out as a validation set, while the remaining k-1 folds are combined to form the training set. The model is fitted on the training folds across a grid of candidate lambda values, and its prediction error is evaluated on the held-out validation fold. After sweeping through all k iterations, the validation errors across all k-folds are averaged for each candidate lambda value, generating a smooth cross-validation error curve as a function of lambda. The hyperparameter value that minimizes the mean validation error is identified as lambda min. To construct even more conservative, resilient models in noisy environments, staff engineers often apply the one standard error rule or 1SE rule. Instead of choosing lambda min, the 1SE rule selects the largest lambda value whose cross-validation error falls within one standard error of the minimum validation error. Choosing this slightly larger lambda value imposes stronger regularization, producing a leaner, simpler model that achieves virtually identical predictive performance while providing greater robustness against distribution shift in production. When working with grouped, time series, or imbalanced datasets, standard k-fold cross-validation can introduce data leakage. To preserve validation integrity, engineers adjust the splitting schema. using stratified k-fold to maintain class proportions across folds, or group k-fold to ensure that observations belonging to the same entity or session are never split across training and validation sets simultaneously. In conclusion, regularization transforms classical linear modeling from a fragile, variance-prone solver into a highly resilient production methodology. By mastering the bias-variance trade-off, enforcing mandatory feature standardization, leveraging L2 ridge shrinkage to stabilize ill-conditioned matrices, applying L1 lasso soft thresholding to drive sparse feature selection, combining both penalties via elastic net grouping, understanding Gaussian and Laplace Bayesian priors, and tuning hyperparameters using k-fold cross-validation with the 1SE rule, software engineers can deploy robust linear models capable of generalizing effectively across high-dimensional feature spaces. Up to this point, our quantitative exploration has focused on regression tasks, predicting continuous real-value targets such as system latency, memory consumption, financial value, or physical velocity. However, a vast domain of modern engineering problems is categorical rather than continuous. We must determine whether an incoming transaction is fraudulent or legitimate, whether a system node is healthy or failing, whether a user will convert or churn, or whether a network packet represents a security threat or benign traffic. These are classification tasks, where the target response is a discrete categorical label. When first encountering binary classification, a developer might attempt to apply standard linear regression by assigning numerical values of 0 and 1 to the two target classes, fitting an ordinary least squares line, and predicting a class label of 1 if the regression output exceeds 0.5. However, forcing linear regression onto classification tasks results in severe structural failures. The first structural failure is that linear regression produces unbounded output predictions extending from negative infinity to positive infinity. Assigning a physical interpretation to a predicted output value of 2.7 or negative 0.4 when the true target is strictly constrained to 0 or 1 is mathematically nonsensical. In engineering pipelines, predictions must represent bounded probabilities bounded strictly between 0 and 1. The second structural failure is extreme sensitivity to leverage outliers. Because ordinary least squares minimizes squared vertical distances, an extreme observation positioned far away from the decision region, such as a legitimate request with exceptionally large payload size, will exert massive leverage on the fitted line. The OLS line swings dramatically toward the outlier to minimize its squared error, shifting the implicit decision boundary and misclassifying a vast swath of normal data points. The third structural failure is violation of homoscedasticity. For a binary target variable following a Bernoulli distribution, the variance of the error term depends directly on the predicted probability, equal to the probability p multiplied by 1 minus p. As predicted probabilities approach 0 or 1, the variance contracts towards 0, but as probabilities approach 0.5, variance reaches its peak. This inherent heteroscedasticity invalidates the standard error assumptions of ordinary least squares. To resolve these fundamental flaws and build a mathematically sound probabilistic classifier, engineers turn to logistic regression. Despite having the word regression in its historical name, logistic regression is a powerful, highly interpretable algorithm explicitly designed for classification. Rather than modeling the binary target outcome directly as a linear function, logistic regression models the probability that a given observation belongs to the positive class. To bridge the gap between a probability bounded strictly between 0 and 1, and a linear combination of features that can range from negative infinity to positive infinity, we utilize a sequence of link function transformations: odds, log odds, and the sigmoid function. First, we define the odds of an event occurring. The odds ratio is calculated as the probability p that the positive event occurs, divided by the probability 1 minus p that it does not occur. While probability is bounded between 0 and 1, the odds ratio maps the output domain onto a non-negative continuous scale ranging from 0 to positive infinity. An event with a probability of 0.5 has an odds ratio of 1. An event with a probability of 0.8 has an odds ratio of 4, meaning it is 4 times more likely to occur than not to occur. Second, to map the odds domain from a non-negative scale onto a fully symmetric scale extending from negative infinity to positive infinity, we take the natural logarithm of the odds ratio. This operation is defined as the logit transformation, or log odds. The logit of a probability p equals the natural logarithm of p divided by 1 minus p. When p is 0, the logit goes to negative infinity. When p is 0.5, the logit is exactly 0. And when p approaches 1, the logit goes to positive infinity. In logistic regression, we assert that the log odds of the positive class is a linear function of the predictor features. The model equation states that the natural logarithm of p divided by 1 minus p equals the intercept plus a linear combination of feature weights. Third, to convert predicted log odds back into an interpretable probability bounded strictly between 0 and 1, we invert the logit equation using algebra. Solving the logit equation for probability p yields the celebrated logistic sigmoid activation function. The probability p of an observation belonging to the positive class is expressed as 1 divided by the quantity 1 plus Euler's number raised to the power of negative x beta, where x beta represents the linear combination of feature weights. The sigmoid function forms a smooth, elegant S-shaped curve. As the linear combination x beta takes large positive values, Euler's number raised to negative x beta approaches 0, causing the sigmoid function to asymptote smoothly toward 1. As x beta takes large negative values, Euler's number raised to negative x beta explodes, causing the denominator to shoot up and forcing the sigmoid output to asymptote smoothly toward 0. When x beta equals exactly 0, the sigmoid function outputs a probability of exactly 0.5. The sigmoid function possesses a vital mathematical property that makes it exceptionally efficient for optimization. Its derivative can be expressed entirely in terms of its own output. The derivative of the sigmoid function with respect to its input z equals the sigmoid of z multiplied by the quantity 1 minus the sigmoid of z. This clean derivative identity significantly simplifies the calculation of loss gradients during model training. To fit the weight parameters of a logistic regression model, we must establish an optimization loss function. A novice developer might consider combining the sigmoid activation function with the familiar mean squared error loss. However, doing so triggers a severe optimization bottleneck. Passing a linear combination through the nonlinear S-curve of the sigmoid function before squaring the error creates a complex, non-convex loss surface littered with shallow plateaus, local minima, and vanishing gradient regions where optimization algorithms get hopelessly stuck. To guarantee a convex loss landscape with a unique global minimum, engineers replace mean squared error with maximum likelihood estimation, or MLE, deriving the binary cross-entropy loss, also known as log loss. Maximum likelihood estimation approaches parameter estimation from a probabilistic viewpoint. We assume that each observed target label y sub I is a random draw from a Bernoulli distribution with parameter p sub I, representing the predicted probability generated by our model. The probability mass function for a single binary observation can be written compactly as p raised to the power of y, multiplied by 1 minus p raised to the power of 1 minus y. When y is 1, the second term collapses to 1, leaving p. When y is 0, the first term collapses to 1, leaving 1 minus p. Assuming that all n observations in our training set are conditionally independent given the features, the likelihood function for the entire dataset equals the product of individual probabilities across all n data points. The likelihood function quantifies the overall probability that our model parameters would generate the exact pattern of target labels observed in our training data. Because multiplying thousands of probabilities together produces vanishingly tiny numbers that cause floating point underflow in computer memory, we take the natural logarithm of the likelihood function, converting the product of probabilities into a sum of log probabilities. To transform the goal from maximizing likelihood to minimizing a loss function suitable for standard optimization routines, we multiply the log likelihood by -1 and divide by the sample size n. This produces the binary cross-entropy loss function. The binary cross-entropy loss function computes the negative average of y times the natural logarithm of predicted probability p, plus 1 minus y times the natural logarithm of 1 minus predicted probability p. Inspecting binary cross-entropy loss reveals a severe penalty structure. Suppose the true target label is 1. The second term drops out, leaving negative log of p. If the model correctly predicts a probability near 1, the log of 1 is 0, resulting in near zero loss. However, if the model confidently misclassifies the observation, predicting a probability near 0, the log of a near zero number goes to negative infinity, causing the loss to explode to massive positive values. This logarithmic penalty severely penalizes confident wrong predictions, forcing the model to adjust its parameters rapidly. Crucially, combining binary cross-entropy loss with the sigmoid activation function restores strict mathematical convexity to the loss surface. The resulting loss landscape is a smooth, bowl-shaped surface in parameter weight space with a guaranteed unique global minimum. To find the optimal weight vector that minimizes binary cross-entropy loss, we take the partial derivative of the loss function with respect to the weight vector beta. Evaluating the gradient using vector calculus yields a strikingly simple result. The gradient vector equals 1 divided by n, multiplied by x transpose times the residual vector p minus y, where p is the vector of predicted probabilities and y is the vector of true target labels. Notice the profound mathematical harmony of this gradient. It has the exact same structural form as the gradient derived for ordinary least squares linear regression, with the raw target prediction replaced by the sigmoid predicted probability. Because the sigmoid equation contains nonlinear exponential terms, setting the binary cross-entropy gradient to 0 does not yield a closed-form analytical matrix solution like the normal equations in linear regression. Logistic regression parameters must be solved using iterative optimization algorithms. While batch gradient descent, stochastic gradient descent, and mini-batch gradient descent can all optimize logistic regression, staff engineers frequently deploy second-order optimization methods for faster convergence on medium-sized datasets, most notably the Newton-Raphson method, also known as iteratively reweighted least squares or IRLS. While first-order gradient descent uses only the gradient vector to take steps down the loss surface, Newton-Raphson utilizes second derivatives by calculating the Hessian matrix. The Hessian matrix H contains all pairwise second-order partial derivatives of the loss function with respect to the parameter weights. For logistic regression, the Hessian matrix is computed as 1 divided by n, multiplied by x transpose times w times x, where W is a diagonal weight matrix whose ith diagonal element equals predicted probability P sub I multiplied by 1 minus P sub I. The Newton-Raphson update rule calculates the new parameter weight vector by taking the current weight vector and subtracting the inverse of the Hessian matrix multiplied by the gradient vector. Near the minimum of a convex surface, Newton-Raphson exhibits quadratic convergence, reaching the exact optimal parameter weights in a handful of iterations compared to hundreds or thousands of steps required by standard first-order gradient descent. For massive high-dimensional feature spaces where computing and inverting the full Hessian matrix becomes computationally prohibitive, engineers deploy quasi-Newton algorithms like LBFGS, which approximate the inverse Hessian using a low-rank history of recent gradient vectors. When deployed in production, a fitted logistic regression model generates continuous predicted probabilities. To convert these continuous probabilities into discrete binary class assignments, we establish a decision threshold, typically defaulting to 0.5. Geometrically, setting the decision threshold to a probability of 0.5 corresponds to finding the region where the linear combination x beta equals exactly 0. The equation x beta equals 0 defines a linear decision boundary, a straight line in two-dimensional feature space, a flat plane in three-dimensional space, or a linear hyperplane in high-dimensional space. Observations positioned on one side of the hyperplane are classified as positive, while observations on the other side are classified as negative. While standard logistic regression creates linear decision boundaries, engineers can construct highly complex nonlinear decision boundaries by combining logistic regression with basis expansion, such as adding polynomial features or spline terms to the input design matrix. A logistic regression model equipped with quadratic feature terms forms parabolic, elliptical, or hyperbolic decision boundaries in feature space while remaining computationally lightweight and fully interpretable. To handle multi-class classification problems where the target variable spans k distinct categories, such as classifying image types, document topics, or diagnostic states, engineers extend binary logistic regression using two primary architectural paradigms: one versus rest and softmax regression. The one versus rest paradigm, also called one versus all, decomposes a k-class classification task into k separate binary classification problems. For each class k, we train an independent binary logistic regression model where class k is treated as the positive class and all remaining k-1 classes are combined to form the negative class. During inference, all k binary models evaluate the input feature vector simultaneously, generating k individual probability estimates. The overall model predicts the final class label corresponding to whichever binary classifier produced the highest probability score. An alternative multi-class approach is one versus one, where we train a separate binary classifier for every unique pair of classes, resulting in k times k-1 divided by two individual models. During inference, each pairwise classifier casts a vote for its predicted class, and the class receiving the majority of votes wins. While one versus one requires training many models, each individual model is trained on a small subset of data containing only two classes, making it useful for algorithms with nonlinear scaling. The most mathematically elegant extension for multi-class classification is softmax regression, also known as multinomial logistic regression. Softmax regression generalizes binary logistic regression to model all k-class probabilities simultaneously in a single unified architecture. Softmax regression maintains k distinct weight vectors, producing k linear score outputs for an input feature vector. To transform these raw, unnormalized scores into a valid probability distribution across all k classes that sums to exactly 1, we apply the softmax activation function. The softmax function computes the predicted probability for class K as Euler's number raised to the raw linear score for class K, divided by the sum of Euler's number raised to raw linear scores across all. To train softmax regression, we replace binary cross-entropy loss with categorical cross-entropy loss. Categorical cross-entropy measures the distance between the true one-hot encoded target distribution and the predicted softmax probability distribution, generating strong loss gradients that update all k-parameter weight vectors simultaneously. Finally, staff engineers must evaluate probability calibration. A well-calibrated classifier is one where the predicted probability score directly reflects true empirical frequency. For instance, if a well-calibrated fraud model assigns a 0.80 probability of fraud to a batch of 100 transactions, exactly 80 of those transactions should turn out to be truly fraudulent. While logistic regression optimized via binary cross-entropy produces naturally well-calibrated probabilities under ideal linear conditions, real-world distribution shifts, feature nonlinearities, or heavy regularization penalties can degrade probability calibration. To restore accurate probability estimates in production, engineers apply post-processing calibration algorithms such as Platt scaling, which fits a secondary logistic regression curve on raw model scores, or isotonic regression, a non-parametric monotonic step function transformation. In conclusion, logistic regression represents a cornerstone of classical classification. By mapping linear combinations of features through the logit and sigmoid transformations, optimizing convex binary cross-entropy loss via gradient or Newton-Raphson methods, defining linear hyperplanes in feature space, extending to multi-class problems via softmax regression, and verifying probability calibration, software engineers can construct blazingly fast, highly reliable, and deeply interpretable classification pipelines for modern production applications. Deploying a machine learning model into production requires far more than training loss optimization and parameter estimation. Once a classifier generates predictions, staff engineers must rigorously evaluate its operational performance. In regression tasks, evaluating error is relatively straightforward using metrics like mean squared error or root mean squared error, which quantify deviation on a continuous scale. In classification tasks, however, evaluating model quality introduces complex operational trade-offs where different types of mistakes carry vastly different business and computational costs. A novice developer's first instinct when evaluating a classification model is to calculate raw classification accuracy, the total number of correct predictions divided by the total number of evaluated observations. While classification accuracy provides an intuitive percentage scale, relying on accuracy in real-world production environments represents one of the most dangerous traps in modern software engineering. The fundamental flaw of raw classification accuracy is its complete vulnerability to the accuracy paradox in imbalanced datasets. Real-world engineering problems are almost never balanced 50-50 across classes. If a developer builds a naive dummy model that contains zero intelligence and simply predicts legitimate for every single incoming transaction, that dummy model will achieve a staggering 99.9% raw classification accuracy. On paper, a 99.9% accuracy score looks exceptional. In reality, the system is a complete operational failure. It catches zero fraudulent transactions, allowing millions of dollars in fraudulent activity to process unchecked. High accuracy creates a false illusion of system health while masking total functional failure. To overcome the illusion of raw accuracy and evaluate classifiers effectively, staff engineers anchor their diagnostic evaluation around the confusion matrix. The confusion matrix is a structured 2x2 grid that partitions all model predictions against actual ground truth target outcomes, categorizing every evaluated instance into one of 4 distinct operational quadrants: true positives, false positives, true negatives, and false negatives. To build a spatial mental model of the confusion matrix, visualize a diagnostic screening process. The first quadrant contains true positives, denoted as TP. The second quadrant contains false positives, denoted as FP. A false positive represents a type 1 statistical error, often called a false alarm. It occurs when the model predicts a positive outcome for an instance that is actually negative, such as flagging a legitimate user checkout as fraudulent or raising a system alert when servers are operating normally. The third quadrant contains true negatives, denoted as TN. A true negative occurs when the model correctly predicts a negative outcome for an instance that is truly negative, such as correctly passing a legitimate user request or confirming that a healthy system node requires no intervention. The fourth quadrant contains false negatives, denoted as FN. A false negative represents a type 2 statistical error, often referred to as a misdetect. By dissecting model predictions into these 4 distinct quadrants, engineers derive specialized performance metrics that isolate specific operational characteristics: precision, recall, and specificity. Precision, also known as positive predictive value, measures the exactness of the positive predictions generated by the model. It is calculated as the number of true positives divided by the sum of true positives and false positives. Precision answers a specific operational question. Of all the instances that the model flagged as positive, what percentage was actually positive? High precision means that when the system raises an alert, engineers can trust with high confidence that the alert is genuine, minimizing time wasted investigating false alarms. Recall, also known as sensitivity or the true positive rate, measures the coverage or completeness of the model's detection capabilities. It is calculated as the number of true positives divided by the sum of true positives and false negatives. Recall answers a different operational question. Of all the actual positive instances that existed in the real world, what percentage did our model successfully catch? High recall means that the system lets very few positive events slip through undetected, minimizing misdetections. Specificity, also known as the true negative rate, measures the model's ability to correctly identify negative instances. It is calculated as the number of true negatives divided by the sum of true negatives and false positives. Specificity quantifies how effectively the model filters out background noise without triggering false alarms. In real-world engineering, precision and recall exist in a state of permanent tension, creating a fundamental operational trade-off. You can easily achieve 100% recall by lowering your model's decision threshold to 0, classifying every single instance as positive. However, doing so floods the system with false positives, causing precision to collapse towards 0. Conversely, you can achieve near 100% precision by raising the decision threshold to an extremely conservative level, classifying only the most obvious cases as positive. But doing so causes false negatives to skyrocket, tanking recall. To summarize this trade-off in a single unified score, developers often reach for the arithmetic mean of precision and recall. However, using an arithmetic mean creates a dangerous evaluation flaw. Consider a broken model that achieves 100% recall by classifying everything as positive, but gets only 1% precision due to massive false alarms. The arithmetic mean of 101 is 50.5%, falsely suggesting moderate performance for a completely useless model. To penalize extreme imbalances between precision and recall, staff engineers use the harmonic mean, known as the F1 score. Unlike the arithmetic mean, the harmonic mean gives disproportionately heavy weight to whichever metric is smaller. If either precision or recall approaches 0, the numerator of the F1 calculation contracts towards 0, causing the overall F1 score to collapse. A model can achieve a high F1 score only if both precision and recall are simultaneously high, making F1 the standard baseline metric for evaluating balanced performance on imbalanced datasets. In many engineering domains, however, precision and recall carry vastly different operational costs, making a 50-50 balanced F1 score suboptimal. For instance, in an automated spam filter, a false positive, moving a critical client contract email into the spam folder, is disastrous, whereas a false negative, letting a minor spam email reach the inbox, is a minor nuisance. In this scenario, engineers prioritize precision over recall. Conversely, in a critical medical diagnostic system or infrastructure failure predictor, a false negative, missing an impending disk crash, is catastrophic, while a false positive, performing unnecessary preventative inspection, is cheap. Here, engineers prioritize recall. To adjust the weighting between precision and recall explicitly, staff engineers deploy the generalized F-beta score. The F-beta score modifies the harmonic mean formula by introducing a weighting parameter, beta. The F-beta score is calculated as 1 plus beta squared, multiplied by precision times recall, divided by the quantity beta squared times precision, plus recall. The parameter beta acts as an explicit dial controlling the relative importance of recall versus precision. Setting beta to 0.5 weights precision twice as heavily as recall, making it ideal for spam filtering or customer-facing automated actions where false alarms incur high costs. Setting beta to 2.0 weights recall twice as heavily as precision, making it the preferred metric for security threat detection, fraud screening, and critical system failure monitoring. To evaluate a classifier's performance across all possible operational decision thresholds simultaneously rather than at a single fixed threshold, staff engineers generate curve-based metrics: the precision recall curve and the receiver operating characteristic curve. A precision recall curve, often abbreviated as the PR curve, plots precision on the vertical axis against recall on the horizontal axis as the decision probability threshold sweeps continuously from 1.0 down to 0.0. At a threshold of 1.0, the model classifies nothing as positive, resulting in high precision and zero recall. As the threshold lowers toward 0.0, recall expands toward 1.0 while precision generally degrades. Integrating the area under the precision recall curve yields the PRAUC score, also known as average precision. PRAUC provides a single scalar value summarizing the classifier's overall trade-off spectrum. Crucially, the baseline of a PR curve for a random dummy classifier equals the prevalence of the positive class in the dataset. In highly imbalanced regimes, such as a dataset with 0.1% positive instances, a random model has a baseline PRAUC of 0.001. Consequently, PR curves are exceptionally sensitive to false positives in rare event domains, making them the gold standard evaluation tool for severe class imbalance. The alternative curve-based metric is the receiver operating characteristic curve, universally known as the ROC curve. The ROC curve plots the true positive rate, which is identical to recall, on the vertical axis against the false positive rate on the horizontal axis across all decision thresholds. The false positive rate is calculated as false positives divided by the sum of false positives and true negatives, representing 1 minus specificity. A random dummy classifier that assigns random probabilities generates a linear diagonal line from the bottom left corner to the top right corner of the ROC space, corresponding to an area under the ROC curve or ROC score of exactly 0.5. A perfect classifier that achieves 100% true positive rate with 0 false positive rate forms a sharp right-angled trajectory reaching the top left corner, yielding a perfect ROC score of 1.0. ROC possesses a fascinating mathematical interpretation from probability theory. The ROC score equals the exact probability that a randomly chosen positive instance will be assigned a higher predicted probability score by the model than a randomly chosen negative instance. This property makes ROC a pure measure of rank ordering capability. If a model ranks all positive instances above all negative instances, its ROC will be 1.0, regardless of whether the raw predicted probabilities are perfectly calibrated between 0 and 1. Furthermore, ROC is completely invariant to monotonic positive transformations of predicted scores, as well as shifts in class distribution prevalence. However, this prevalence invariance contains a hidden engineering trap. In extremely imbalanced datasets with millions of negative instances, the denominator of the false positive rate, true negatives plus false positives, is massive. Millions of false positives can accumulate without significantly increasing the false positive rate, making an ROC curve appear misleadingly optimistic. Therefore, staff engineers use ROC curves for general rank ordering evaluation on balanced or moderately imbalanced data, but switch strictly to PR curves when assessing severe class imbalance. Once a classifier is trained and its performance evaluated, engineers must select the optimal operational decision threshold for production deployment. Accepting the default threshold of 0.5 is rarely optimal. To select an optimal threshold programmatically, engineers apply quantitative selection rules such as Uden's J statistic or cost-sensitive threshold optimization. Uden's J statistic identifies the threshold that maximizes the vertical distance between the ROC curve and the random diagonal line. It is calculated as sensitivity plus specificity minus 1. Maximizing Uden's J statistic finds the point that balances true positives and true negatives equally. In commercial production environments, however, decision thresholds should be driven by explicit financial and operational cost matrices. Let C sub FP represent the specific monetary or operational cost of a false positive, such as paying a customer service representative $5 to manually review a falsely flagged account. Let C sub FN represent the cost of a false negative, such as absorbing a $100 financial loss from an uncaught fraudulent transaction. The total expected operational cost of a deployment is computed as the cost of a false positive multiplied by the number of false positives, plus the cost of a false negative multiplied by the number of false negatives. By evaluating total expected cost across a fine grid of candidate probability thresholds, engineers discover the cost-minimizing threshold P star. Mathematically, the optimal cost-sensitive decision threshold P star can be derived directly as the ratio of false positive cost to the sum of false positive cost and false negative cost. If a false negative costs 20 times more than a false positive, the optimal decision threshold drops to 0.047. Setting the threshold to 0.047 instructs the system to flag an instance as positive if its predicted probability exceeds roughly 4.7%, drastically reducing total operational financial loss even though raw classification accuracy decreases. Finally, staff engineers evaluate probability calibration using metrics like the Breyer score. While ROCUC evaluates whether a model correctly ranks positive instances above negative ones, it does not guarantee that the output scores represent true physical probabilities. The Breyer score measures the mean squared difference between predicted probability scores and true binary outcomes across all observations. It is calculated as 1 divided by n, multiplied by the sum of squared differences between predicted probability p sub I and binary target y sub I. The Breyer score acts as the classification equivalent of mean squared error, ranging from 0 for a perfectly calibrated and accurate model to 1 for a completely inverted model. Using mathematical decomposition, the Breyer score can be broken down into 3 distinct components: reliability, resolution, and uncertainty. Reliability measures how closely predicted probabilities match observed class frequencies across probability bins. Resolution measures how much the model's predictions deviate from the overall sample base rate. Uncertainty measures the inherent randomness of the underlying data-generating process. In conclusion, evaluating classical classification models requires a comprehensive diagnostic suite. By rejecting raw accuracy in favor of the confusion matrix, balancing precision and recall using the harmonic F1 and cost-weighted F-beta scores, leveraging PR curves for imbalanced data and ROC curves for rank ordering, optimizing decision thresholds using explicit cost matrices, and auditing probability calibration via the Breyer score, software engineers can ensure that deployed classification models deliver optimal operational and economic value in production systems. Parametric models like linear and logistic regression attempt to fit a single global functional surface, a straight line, flat hyperplane, or smooth sigmoid curve, across an entire feature space. While global parametric models excel when true underlying relationships are smooth and continuous, real-world engineering workflows frequently operate on discrete conditional logic. System routers evaluate nested rules, database query planners follow branching logic execution paths, and diagnostic algorithms trigger actions based on threshold boundaries. To model these nonlinear, rule-based decision processes natively, staff engineers deploy decision trees. A decision tree is a non-parametric supervised learning algorithm that partitions a high-dimensional feature space into a collection of non-overlapping, axis-aligned hyperrectangular regions. Unlike linear models, which weight and combine all input features simultaneously into a unified equation, a decision tree evaluates features sequentially through a series of nested conditional splits. To build a spatial mental model of a decision tree, visualize a high-dimensional feature space containing data points. The root node of the tree selects a single predictor feature and a specific numerical threshold value, drawing an orthogonal hyperplane that cuts the feature space cleanly into 2 subregions. Each child node then selects another feature and threshold, slicing its localized subregion further. This recursive partitioning continues down the tree until terminal subregions, known as leaf nodes, are created. For any query point passing down the tree, its feature values dictate which conditional branch to follow until it settles into a specific leaf node. The prediction generated by the decision tree is completely constant across all points falling within that specific leaf node. In a regression tree, the leaf prediction equals the sample mean of the training target values contained within that leaf node. In a classification tree, the leaf prediction equals the majority class vote, or the empirical class probability distribution of the training instances assigned to that leaf. The foundational algorithm for constructing decision trees is the classification and regression tree algorithm, universally known as CART. CART constructs binary trees by performing recursive binary splitting. Recursive binary splitting is a greedy, top-down optimization process. It is described as top-down because it begins at the root of the tree and sequentially splits the feature space downwards. It is described as greedy because at each individual step, the algorithm selects the single best feature and split threshold that maximizes immediate impurity reduction at that specific node, without considering whether a different split might lead to a superior overall tree structure several levels deeper down the branch. To execute a split at a given node, CART evaluates every candidate predictor feature j from feature 1 to feature p. For a continuous numeric feature j, the algorithm sorts all distinct observed values in ascending order and considers every midpoint between adjacent values as a candidate numerical split threshold. S. In a regression tree, CART selects the feature j and split threshold s that minimizes the sum of residual sum of squares across the resulting left and right child regions. Equivalently, the algorithm maximizes variance reduction. Variance reduction computes the total sample variance of the target variable in the parent node minus the weighted sum of target sample variances in the left and right child nodes. The algorithm searches across all p features and all candidate thresholds to find the pair that yields the largest reduction in target variance. In a classification tree, using raw residual sum of squares is inappropriate. A novice developer might consider evaluating candidate splits by calculating the reduction in raw classification error rate, the proportion of training observations in a node that do not belong to the majority class. However, raw classification error rate is insufficiently sensitive for growing deep decision trees. To understand why raw classification error rate fails during tree growth, consider a node containing 80 observations of class A and 20 observations of class B, giving a raw error rate of 20%. Suppose a candidate split divides the node into two child nodes. The first child contains 60 class A observations and 0 class B observations, achieving 100% class purity. The second child contains 20 class A and 20 class B observations, with a 50% error rate. The weighted average error rate across both child nodes remains exactly 20%. Evaluating the split using raw classification error suggests zero improvement, even though the split created a perfectly pure child node that isolates class A completely. To reward splits that increase node purity, staff engineers use mathematically sensitive node impurity measures, Gini impurity and Shannon entropy. Gini impurity, denoted as G, quantifies the probability that a randomly chosen instance from a node would be incorrectly labeled if it were randomly labeled according to the distribution of class labels within that node. For a node M with k classes, Gini impurity is calculated as the sum across all k classes of predicted class probability p sub mk multiplied by 1 minus p sub mk. Mathematically, this equals 1 minus the sum of squared class probabilities across all k classes. If a node is completely pure, containing observations belonging exclusively to a single class, the class probability for that class is 1 and all other class probabilities are 0. The sum of squared probabilities equals 1, resulting in a Gini impurity of exactly 0. Conversely, if a node contains an equal distribution across k classes, Gini impurity reaches its maximum value, representing maximum node disorder. An alternative purity metric is Shannon entropy, derived from information theory. Entropy, denoted as D, measures the average amount of information, or uncertainty, contained within a node's class distribution. Entropy is calculated as the negative sum across all k classes of predicted class probability p sub mk multiplied by the logarithm base 2 of p sub mk. Like Gini impurity, entropy equals exactly 0 for a completely pure node with 0 uncertainty, and reaches its peak when class probabilities are uniformly distributed. When a decision tree uses entropy to evaluate splits, the reduction in total entropy achieved by partitioning a node is defined as information gain. While information gain is highly effective, it exhibits a known statistical bias toward multi-level categorical features with many distinct values, such as user ID or zip code. A feature with unique values for every row will yield 100% information gain, creating pure single-instance leaf nodes without capturing true underlying relationships. To correct for this categorical split inflation, algorithms like C4.5 replace raw information gain with the gain ratio. The gain ratio divides information gain by the split information metric, imposing an explicit entropy penalty on splits that produce many fine-grained subbranches. Both Gini impurity and Shannon entropy are strictly concave functions of class probabilities. Because of their mathematical concavity, splitting a node into two child nodes will almost always reduce the weighted average impurity, even when raw classification error remains unchanged. Consequently, Gini impurity and entropy act as sensitive optimization drivers that aggressively favor splits that isolate pure class clusters. In modern machine learning libraries, Gini impurity is typically the default splitting criterion because it avoids computing logarithmic functions, making it computationally faster to evaluate across millions of candidate splits. Evaluating candidate splits across continuous features introduces computational complexity considerations. For a dataset containing n observations and p features, evaluating all split candidates at a node requires sorting the feature values for each predictor, taking time proportional to p times n log n. Once features are sorted, sweeping across candidate thresholds to evaluate Gini impurity or RSS takes linear time proportional to n. As a tree grows deeper, the number of observations assigned to subnodes shrinks, speeding up local split evaluations, but overall tree construction remains computationally intensive for massive high-dimensional datasets. To process discrete categorical features in decision trees, CART evaluates candidate splits by partitioning the discrete category states into two disjoint subsets. For a categorical variable with C unique categories, there are 2 raised to the power of C-1-1 candidate binary partitions. If a category feature has dozens of unique levels, evaluating all candidate subsets becomes computationally intractable. To bypass this exponential expansion, algorithm implementations sort the categorical levels according to their mean target value or class proportion, reducing the candidate search space from exponential down to linear order C. Decision trees also possess a built-in mechanism for handling missing feature values during inference through surrogate splits. When a query instance arrives at a node and its primary splitting feature value is missing, the decision tree does not crash or require imputation. Instead, it inspects a ranked list of pre-computed surrogate features, secondary features that produce split boundaries most strongly correlated with the primary split. The instance follows the surrogate split rule to route down the tree smoothly. Despite their structural elegance, fully grown, unconstrained decision trees suffer from a massive engineering flaw: catastrophic overfitting and extreme variance. If a decision tree is allowed to grow without depth constraints, it will continue splitting nodes recursively until every single leaf node contains a single data point or achieves 100% purity. Such a tree achieves 0 residual sum of squares or 0 Gini impurity on the training set. However, the fully grown tree has memorized every random noise artifact, measurement error, and outlier in the training data. The resulting model forms tiny, convoluted rectangular islands in feature space, creating a fragile architecture that fails completely when evaluating unseen production data. To prevent decision trees from overgrowing, developers often set early stopping hyperparameters, setting a maximum tree depth using max_depth, requiring a minimum number of samples to split an internal node using min_samples_split, or enforcing a minimum number of samples per leaf node using min_samples_leaf. However, relying exclusively on early stopping hyperparameters contains a subtle structural flaw known as the look-ahead problem. A greedy decision tree might encounter an early split that yields virtually zero immediate impurity reduction, causing an early stopping rule to terminate tree growth prematurely. Yet, if the tree had been allowed to execute that seemingly useless split, the very next split downstream might have produced massive impurity reduction, uncovering deep structural patterns. Early stopping rules miss these deep patterns because they cannot look ahead. To solve the look-ahead problem, staff engineers do not terminate tree growth early. Instead, they allow the decision tree to grow fully into a large saturated tree, T_0, and then apply minimal cost complexity pruning, also known as alpha pruning. Cost complexity pruning prunes back a fully grown tree mathematically by defining a regularized objective function that balances goodness of fit against tree structural complexity. The cost complexity objective function minimizes the total unregularized subtree impurity plus a complexity penalty scalar, alpha, multiplied by the total number of leaf nodes, denoted as absolute T. The hyperparameter alpha acts as a regularization dial controlling tree size. If alpha is set to 0, the complexity penalty vanishes, and the optimal tree remains the fully grown saturated tree T_0. As alpha increases above 0, the penalty per leaf node becomes increasingly expensive, forcing the pruning algorithm to collapse weak subtrees with minor impurity reductions back into single leaf nodes. If alpha becomes extremely large, the entire tree collapses down to a single root node. To prune the tree efficiently across continuous values of alpha, CART utilizes weakest link pruning. Weakest link pruning demonstrates that as alpha increases continuously from 0, the sequence of optimal subtrees forms a nested hierarchy. The algorithm calculates the collapse threshold for every internal node, the exact value of alpha where collapsing that node's subtree produces less cost complexity penalty than keeping it. The algorithm sequentially prunes the weakest link internal nodes, generating a small sequence of candidate subtrees. Engineers apply k-fold cross-validation across this candidate sequence to select the optimal alpha value, identifying a pruned decision tree that achieves optimal generalization performance. From a low-level system design perspective, deploying decision trees in low-latency production APIs requires optimizing memory layout and CPU cache locality. Naive implementations structure decision trees as pointer-chasing graph nodes, where each node is an object allocated on the heap containing memory pointers to left and right child nodes. Pointer chasing causes frequent CPU cache misses, degrading inference latency. High-performance production engines flatten decision trees into contiguous memory arrays or compiled bytecode, storing feature indices and split thresholds in contiguous memory blocks. Traversing a flattened array utilizes CPU prefetching hardware, accelerating real-time inference latency down to submicrosecond levels. Pruned decision trees offer exceptional interpretability. Because a decision tree consists of sequential threshold checks, a trained model can be exported directly into plain nested if-else code blocks. This transparency makes decision trees invaluable in audited environments, such as financial credit scoring or medical software devices, where engineers must prove precisely why a specific automated decision was made. Furthermore, decision trees are completely invariant to monotonic feature transformations. Standardizing, normalizing, or taking logarithms of input features does not alter the relative rank ordering of data points, leaving the computed split thresholds and tree topology completely unchanged. However, decision trees possess severe structural limitations that staff engineers must carefully manage. First, decision trees struggle to model smooth linear or diagonal decision boundaries. Because every split is strictly orthogonal to a single feature axis, approximating a simple 45-degree diagonal decision boundary requires a decision tree to construct a jagged, staircase-like sequence of dozens of orthogonal splits, introducing unnecessary complexity. Second, decision trees suffer from extreme structural instability, known as high sample variance. Because top-level splits dictate the downstream partitioning of all subsequent subnodes, a tiny perturbation in the training dataset, such as deleting a few data points, can cause the root node to select a completely different feature. This top-level shift cascades down the entire hierarchy, causing the overall tree topology, split rules, and leaf predictions to flip dramatically. In conclusion, decision trees represent a foundational non-parametric paradigm. By executing recursive binary splitting using CART, evaluating splits via Gini impurity, Shannon entropy, or gain ratio, handling missing data with surrogate splits, preventing over-memorization using cost complexity alpha pruning, optimizing memory layouts for CPU cache locality, and exporting transparent nested if-else logic, software engineers can construct highly interpretable models. Mastering the strengths and variance limitations of individual decision trees paves the exact theoretical foundation required to understand modern ensemble algorithms. In our analysis of decision trees, we discovered a major architectural paradox. An individual decision tree possesses low statistical bias, capable of adapting to complex nonlinear boundaries, yet it suffers from extreme variance and sample instability. A minor shift in training data can flip the root node split, restructuring the entire tree hierarchy. In high-stakes engineering environments, relying on a single high-variance model is an operational risk. To eliminate this instability without sacrificing nonlinear modeling power, staff engineers transition from single estimators to ensemble methods. Ensemble methods operate on a fundamental wisdom of the crowd principle. Combining the predictions of multiple individual base estimators produces a composite metamodel that is far more accurate, stable, and resilient than any single constituent model. The foundational ensemble framework for variance reduction is bootstrap aggregating, universally known as bagging. Bagging directly targets variance reduction by leveraging the statistical property of averaging. Recall from introductory statistics that if we have B independent, identically distributed random variables, each with a variance of sigma squared, the variance of their sample mean equals sigma squared divided by B. Averaging B independent models reduces prediction variance by a factor of B without increasing bias. In real-world machine learning pipelines, however, we do not have B independent training datasets gathered from the environment. We typically possess a single finite training dataset of n observations. To simulate drawing B independent datasets from the true population distribution, bagging utilizes bootstrap sampling. A bootstrap sample is generated by taking the original training dataset of n observations and randomly sampling n data points with replacement. Sampling with replacement means that after a data point is selected, it is placed back into the candidate pool, allowing it to be selected again in the same sample. From a combinatorial probability standpoint, bootstrap sampling possesses fascinating properties. The probability that any specific single observation is not chosen in a single random draw equals 1 minus 1 divided by n. For a bootstrap sample of size n, the probability that an observation is completely omitted from the sample equals the quantity 1 minus 1 divided by n raised to the power of n. As the dataset size n grows large, this mathematical expression converges rapidly to 1 divided by Euler's number, which equals approximately 36.8%. This probability reveals a critical insight. Each bootstrap sample contains roughly 63.2% of the unique original training observations, while the remaining 36.8% of observations are left out completely. These omitted observations are designated as out-of-bag observations, or OB data. In the bagging architecture, we generate B-independent bootstrap samples from our original dataset. We then train a separate, unconstrained, deep decision tree on each of the B bootstrap samples, resulting in an ensemble of B-based decision trees. To generate a prediction for a fresh query point, bagging executes the aggregation phase. In a regression task, bagging feeds the query point into all B decision trees simultaneously and computes the unweighted arithmetic average of their individual predictions. In a classification task, bagging aggregates predictions using majority voting, where each tree casts a vote for its predicted class and the winning class is selected, or by averaging predicted class probability distributions across all trees. To understand the mathematical mechanics of variance reduction in bagging, consider an ensemble of B models where each individual model has a prediction variance of sigma squared, and the pairwise correlation coefficient between the predictions of any two trees is denoted as ρ. The total variance of the ensemble's aggregate mean prediction can be expressed mathematically as ρ times sigma squared, plus the quantity 1 minus ρ divided by B, multiplied by sigma squared. Inspecting this variance reduction formula reveals a fundamental structural bottleneck in standard bagging. The second term, 1 minus ρ divided by B times sigma squared, shrinks continuously towards 0 as we increase the number of trees B. However, the first term, ρ times sigma squared, depends entirely on the intertree correlation coefficient ρ, and is completely unaffected by adding more trees. If the decision trees in a bagging ensemble are strongly correlated with one another, meaning ρ is large, the variance reduction of bagging hits a strict lower bound governed by ρ times sigma squared. Adding thousands of additional trees provides zero further variance reduction if those trees make identical errors. Standard bagging suffers from high intertree correlation whenever a dataset contains one or two overwhelmingly dominant predictor features. Consider a dataset where feature 1 has a massive relationship with the target variable compared to all other predictors. When building standard bagging trees across B bootstrap samples, virtually every single tree will independently select feature 1 as its root node split. Because all B trees share the exact same top-level split hierarchy, their downstream structures remain strongly correlated, keeping ρ high and severely limiting the variance reduction benefits of bagging. To break this structural bottleneck and drive the intertree correlation coefficient ρ down towards 0, staff engineers deploy the random forest algorithm. Random forest extends bootstrap aggregating by introducing a secondary layer of explicit randomization known as the random subspace method, or feature randomization. In standard bagging, when a decision tree evaluates candidate splits at a node, it considers all P predictor features in the dataset. In a random forest, whenever a decision tree evaluates a split at any node, the algorithm randomly samples a small subset of M predictor features from the total P features, and restricts the tree to select its split strictly from among those M candidate features. The hyperparameter M dictates the degree of feature randomization. For classification tasks, the standard engineering default sets M to the square root of total features P. For regression tasks, the standard default sets M to P divided by 3. By forcing each node to choose its split from a small random subset of features, random forest prevents dominant features from monopolizing top-level splits across the ensemble. If a dominant feature is excluded from the random subset M at a given node, the tree is forced to explore alternative suboptimal features. This feature randomization decorrelates the decision trees across the forest, driving the pairwise intertree correlation coefficient ρ down towards 0. As ρ approaches 0 in the variance reduction formula, the first term vanishes, allowing the overall ensemble variance to collapse towards sigma squared divided by b. Random forests achieve extraordinary variance reduction, smoothing out the jagged decision boundaries of individual decision trees into robust, highly accurate prediction surfaces while maintaining the low bias of deep trees. A major operational benefit of random forests is free, built-in validation through out-of-bag, OB, error estimation. In traditional workflows, evaluating model generalization requires setting aside a validation dataset or executing computationally expensive k-fold cross-validation, which retrains models k separate times. Random forests eliminate this computational overhead by leveraging the 36.8% of OB data naturally created during bootstrap sampling. To calculate the out-of-bag error score, the algorithm iterates through each observation I in the training set. It identifies the subset of trees in the forest that were trained on bootstrap samples that omitted observation I. The algorithm passes observation I through only this OB subset of trees, averages their predictions, and computes the validation error. Repeating this process across all n observations yields the overall OB error. Statistically, OB error estimation provides an unbiased evaluation of generalization error that tracks k-fold cross-validation performance almost perfectly. Because OB evaluation occurs naturally during model training without refitting trees, staff engineers use OB error to monitor model performance and tune hyperparameters in real time, saving massive computational resources. Beyond prediction and validation, random forests construct a powerful non-parametric similarity metric known as the proximity matrix. The proximity matrix is an n-by-n matrix that quantifies topological closeness between every pair of observations in a dataset. To construct the proximity matrix, all n training observations are passed down every tree in a trained random forest. If observation I and observation j land in the exact same leaf node in a specific tree, their pairwise proximity score increases by 1. After accumulating counts across all B trees, proximity scores are normalized by dividing by B. The resulting proximity matrix measures how frequently pairs of data points share subspaces across randomized feature hierarchies. Staff engineers utilize the proximity matrix for multidimensional scaling visualization, unsupervised clustering, outlier detection, and advanced missing value imputation, where missing feature values are imputed as weighted averages of nearest neighbors defined by proximity scores. Furthermore, the random partitioning logic of decision trees underpins specialized anomaly detection architectures, most notably isolation forests. An isolation forest operates on a clever structural principle. Anomalous, rare data points possess extreme feature values that make them far easier to isolate from normal data points. Instead of building supervised trees to predict a target, and isolation forest constructs an ensemble of completely random decision trees that choose features and split thresholds at random. Normal, clustered data points require many recursive splits to isolate into single leaf nodes, resulting in long path lengths from the root node. Anomalous data points, being isolated in sparse feature regions, are separated quickly near the top of the tree, resulting in short path lengths. By measuring average path length across an ensemble of random trees, isolation forests detect system anomalies, fraud spikes, and hardware failures in linear time complexity without requiring labeled training targets. To contrast ensemble strategies, staff engineers distinguish bagging from boosting. While bagging builds independent deep trees in parallel to reduce variance, boosting builds shallow weak trees sequentially in series to reduce bias. In boosting, each new tree is trained specifically on the residual errors or reweighted instances produced by preceding trees. Understanding both paradigms equips engineers to choose between parallel variance reduction via random forests and sequential bias reduction via gradient-boosted trees. To maintain system interpretability across an ensemble of hundreds of randomized trees, staff engineers calculate feature importance metrics: mean decrease in impurity and permutation feature importance. Mean decrease in impurity, universally known as MDI or Gini importance, measures the total structural contribution of each feature across the entire forest. Whenever a feature is selected to split a node in any tree within the forest, the algorithm calculates the resulting weighted impurity reduction using Gini impurity or variance reduction and adds it to that feature's cumulative importance score. After all trees are built, cumulative scores are normalized to sum to 1. While MDI is blazingly fast to compute during training, it contains a well-documented statistical bias. MDI systematically overestimates the importance of continuous features or high cardinality categorical features with many unique levels. High cardinality features present many candidate split thresholds, giving CART more opportunities to execute splits that yield minor random impurity reductions on the training set. To obtain an unbiased, model-agnostic assessment of feature importance, staff engineers rely on permutation feature importance. Permutation feature importance evaluates feature importance on held-out validation data or OB samples after model training is complete. To compute the permutation importance for feature J, the algorithm first records the baseline prediction error of the fitted random forest on the validation set. Next, it takes the column corresponding to feature J and randomly shuffles its values across all validation rows, breaking the true relationship between feature J and the target while preserving the marginal distribution of all other features. The algorithm then passes the modified dataset through the model and measures the resulting increase in prediction error. If feature J is critically important to the model, shuffling its values destroys key predictive information, causing validation error to skyrocket. If feature J is irrelevant or redundant, shuffling its values produces negligible impact on validation error. Permutation feature importance measures the exact drop in model performance caused by corrupting a feature, providing an accurate, unbiased ranking of real-world feature impact. For applications requiring ultra-fast training speeds or even greater variance reduction, engineers turn to extremely randomized trees, commonly known as extra trees. Extra trees takes randomization a step further than random forests. While random forests select split thresholds deterministically by searching for the optimal threshold among the randomized feature subset M, extra trees selects split thresholds completely at random for each candidate feature, and picks the best of those randomly generated thresholds. Randomizing split thresholds eliminates the computationally expensive sorting and threshold sweeping operations required by standard CART nodes, accelerating model training speeds dramatically. Furthermore, threshold randomization introduces additional randomness that decorrelates trees even further, reducing ensemble variance at the cost of a minor increase in bias. In production engineering, configuring random forests involves tuning key structural hyperparameters, n_estimators, max_features, max_depth, min_samples_leaf, and bootstrap. Increasing the number of trees, controlled by n_estimators, never causes a random forest to overfit. Adding more trees simply provides a more precise Monte Carlo approximation of the aggregate ensemble expectation, continually smoothing prediction variance until performance asymptotically stabilizes. The only cost of setting n_estimators too high is increased computational memory footprint and inference latency. From an architectural deployment perspective, random forests represent an embarrassingly parallel workload. Because every tree in the forest is constructed completely independently on its own bootstrap sample, model training scales linearly across arbitrary CPU cores or distributed clusters. Engineers leverage multi-threading libraries to train hundreds of trees concurrently, maximizing hardware utilization. However, staff engineers must manage the inference memory footprint and latency constraints of random forests in production. Unlike a linear regression model that collapses into a compact vector of p-weights, a random forest containing 500 deep decision trees can require gigabytes of RAM to store node pointer structures, with inference requiring hundreds of sequential tree traversals. To optimize production latency, engineers prune forest size down to the minimum number of trees required for asymptotic stability, optimize tree depth, or distill ensemble knowledge into fast, compact neural networks or gradient-boosted decision trees. In conclusion, ensemble methods represent a powerful paradigm shift from individual fragile estimators to resilient collective architectures. By leveraging bootstrap aggregating to reduce prediction variance, applying feature randomization in random forests to decorrelate trees, utilizing out-of-bag error for zero-overhead validation, computing proximity matrices for unsupervised cluster structure, deploying isolation forests for anomaly detection, auditing feature importance via MDI and permutation testing, and scaling training across parallel CPU cores, software engineers can construct highly robust, nonlinear classification and regression engines for mission-critical production systems. In our previous analyses, we explored how decision trees partition feature space using orthogonal step boundaries, and how logistic regression fits probabilistic hyperplanes via maximum likelihood estimation. Support vector machines, universally known as SVMs, take a radically different approach to classification. Rather than focusing on probabilistic distributions or recursive axis-aligned splits, support vector machines operate on a pure geometric philosophy, constructing optimal hyperplanes that maximize the physical geometric margin between distinct classes. To understand the geometric philosophy of support vector machines, begin with the simple case of linearly separable binary data. Suppose we have a dataset containing two classes of data points that can be completely separated by a straight line or flat hyperplane in feature space. Notice that there is not merely a single separating hyperplane that divides the two classes. In fact, an infinite number of different separating hyperplanes can be drawn between two linearly separable clusters, each achieving 100% training classification accuracy. However, Fitting an arbitrary separating hyperplane that passes extremely close to one cluster of data points leaves the model highly vulnerable to small noise variations in future production data. Support vector machines resolve this choice by defining the maximal margin classifier. The maximal margin classifier selects the unique separating hyperplane that is farthest away from the closest training observations of both classes. To build a spatial mental model of the maximal margin classifier, visualize drawing a separating hyperplane through feature space. Next, inflate a parallel boundary corridor outward symmetrically on both sides of the hyperplane until the expanding corridor first makes contact with data points from either class. The total width of this expanded street or corridor is defined as the geometric margin. The central line of the corridor represents the decision boundary, defined mathematically by the equation W transpose x plus b equals 0, where W is the weight vector perpendicular to the hyperplane and b is the intercept scalar offset. The signed perpendicular distance from any training data point x sub I to the decision boundary is calculated as y sub I multiplied by the quantity W transpose x sub I plus b, divided by the Euclidean norm of W, where y sub I represents class labels assigned as +1 or -1. The goal of the maximal margin classifier is to maximize the geometric margin width, which equals 2 divided by the Euclidean norm of W, subject to the constraint that every training data point falls on the correct side of the margin corridor. Mathematically, maximizing 2 divided by the norm of W is equivalent to minimizing 1/2 of the squared Euclidean norm of W, subject to linear inequality constraints requiring that y sub I times the quantity W transpose x sub I plus b is greater than or equal to 1 for all n observations. Minimizing 1/2 of the squared norm of W subject to linear inequality constraints is a classic convex quadratic programming problem. Quadratic programming problems possess a smooth, convex parabolic objective surface with a single unique global minimum, eliminating the danger of getting trapped in local dips. Inspecting the solution to the maximal margin classifier reveals a profound structural discovery. The orientation and position of the optimal separating hyperplane depend exclusively on a tiny subset of training observations located directly on the outer edges of the margin corridor. These critical edge observations are defined as support vectors. Support vectors are the data points that satisfy the inequality constraint with exact equality, where y sub I times the quantity W transpose x sub I plus b equals exactly 1. All other training data points located outside the margin corridor contribute 0 influence to the position of the decision boundary. You could delete 99% of the non-support vector data points from the training set, refit the model, and obtain the exact same separating hyperplane. Support vectors hold up the decision boundary, giving the algorithm its name. However, the maximal margin classifier relies on 2 restrictive assumptions: that the training data is strictly linearly separable, and that the dataset contains 0 noisy outliers. In real-world engineering environments, training data is almost never perfectly linearly separable, and noise artifacts are common. If a single noisy negative observation strays into the positive cluster, the maximal margin classifier fails completely, rendering strict linear separation impossible. To handle non-separable real-world data and construct models that are robust against noise, staff engineers extend the maximal margin classifier to the soft margin classifier, also known as the support vector classifier. The soft margin classifier accommodates overlapping classes and noise by introducing non-negative slack variables, denoted as 11 sub I. A slack variable quantifies how much a specific observation is allowed to violate the strict margin boundary. If an observation has a slack variable of 0, it lies cleanly on or outside its correct margin boundary. If a slack variable is between 0 and 1, the observation lies inside the margin corridor, but remains on the correct side of the decision boundary, representing a correct classification within the margin. If a slack variable exceeds 1, the observation has crossed over to the wrong side of the decision boundary, representing a misclassified instance. The primal objective function of the soft margin classifier balances margin maximization against total slack penalty. The objective function minimizes 1/2 of the squared Euclidean norm of W, plus a regularization hyperparameter, C, multiplied by the sum of slack variables across all n observations, subject to modified margin constraints. The hyperparameter C acts as a vital operational dial controlling the trade-off between margin width and training error tolerance. Setting C to a large value imposes a severe penalty on slack variables, forcing the algorithm to minimize margin violations aggressively. This produces a narrow margin corridor with low training bias, but high model variance, making the classifier sensitive to individual noise points. Conversely, setting C to a small value relaxes the slack penalty, allowing more data points to enter or cross the margin corridor. This produces a wide, forgiving margin corridor with higher training error tolerance. While this increases training bias, it dramatically reduces model variance, creating a smooth, stable decision boundary that generalizes effectively across noisy production environments. When training support vector machines on imbalanced datasets, staff engineers adjust the slack penalty by assigning class-weighted C parameters. Instead of using a single scalar C for all data points, class-weighted SVMs maintain separate C weights for positive and negative classes. Setting a larger C penalty for the minority positive class forces the optimization algorithm to penalize minority class margin violations heavily, preventing the decision boundary from getting pushed over and ignoring the minority class. To unlock the full mathematical power of support vector machines and handle high-dimensional or nonlinear feature spaces, engineers transform the primal quadratic programming problem into its dual formulation using Lagrange multipliers. For each of the n linear inequality constraints in the primal problem, we introduce a non-negative dual variable or Lagrange multiplier alpha sub I. Constructing the Lagrangian function and applying vector calculus yields the Keras-Kuhn-Tucker or KKT optimality conditions. The KKT conditions establish 3 critical structural properties. First, the parameter weight vector W can be expressed as a linear combination of training feature vectors. W equals the sum across all n observations of alpha sub I times y sub I times x sub I. Second, the dual parameters alpha sub I must satisfy complementary slackness, meaning that alpha sub I can be non-zero only for support vectors that lie on or inside the margin boundary. Third, the dual formulation replaces the original weight vector W with the dual parameters alpha sub I. The dual objective function of a support vector machine maximizes the sum of alpha sub I minus 1/2 of the double sum across all pairs of observations I and j of alpha sub I times alpha j times y sub I times yj, multiplied by the inner dot product of feature vectors x sub I transpose x sub j, subject to dual constraints. Examining the dual objective function reveals the most important mathematical insight in support vector machine theory. The optimization objective and subsequent prediction calculations depend exclusively on inner dot products between feature vectors, written as x sub I transpose x sub j. The raw feature coordinates themselves never appear independently. They enter the algorithm strictly through pairwise scalar inner products. This inner product dependency enables the celebrated kernel trick. Suppose a dataset is non-linearly separable in its original low-dimensional feature space, such as two concentric rings of data points where a straight line cannot separate the inner ring from the outer ring. To separate nonlinear data using a linear hyperplane, an engineer could explicitly map input features into a higher dimensional space using a transformation function phi of x. In a higher dimensional space, the nonlinear rings become linearly separable by a flat hyperplane. However, explicitly transforming high-dimensional features quickly triggers an insurmountable computational bottleneck. If mapping features into a million-dimensional space requires computing and storing million-element vectors for every data point, memory consumption explodes and computing pairwise inner products takes massive operational time. The kernel trick completely bypasses this high-dimensional computational bottleneck. By Mercer's theorem, if a function k of x sub I and x sub j is a continuous, symmetric, positive definite kernel function, it calculates the exact inner product of feature vectors in a high-dimensional Hilbert space without ever explicitly computing or storing the transformed feature coordinates. Mathematically, a kernel function evaluates the inner product phi of x sub I transpose phi of x sub j directly in a single mathematical step using low-dimensional input vectors. The algorithm operates implicitly in an infinite-dimensional feature space while performing all calculations in low-dimensional space. Staff engineers select from several standard kernel functions depending on data geometry. The linear kernel computes the standard dot product x transpose z. It is computationally blazingly fast and optimal when feature dimensionality p is already large relative to sample size n, such as in high-dimensional text classification. The polynomial kernel computes the quantity x transpose z plus c raised to a power degree d. It projects data into a polynomial feature space of degree d, capturing nonlinear interactions up to degree d. The radial basis function kernel, universally known as the RBF kernel or Gaussian kernel, is the most popular nonlinear kernel in machine learning. The RBF kernel computes Euler's number raised to negative gamma multiplied by the squared Euclidean distance between x and z. The RBF kernel possesses extraordinary geometric properties. Mathematically, expanding the Gaussian exponential via Taylor series reveals that the RBF kernel implicitly maps input data into an infinite-dimensional feature space. The hyperparameter gamma in the RBF kernel dictates the radius of influence of individual support vectors. Gamma represents the inverse variance of the Gaussian distribution. Setting gamma to a large value contracts the radius of influence, creating tight, highly localized decision boundaries around individual support vectors. Large gamma values allow the model to fit intricate, multi-pocket decision regions, but risk severe overfitting and high variance. Setting gamma to a small value expands the radius of influence, smoothing out localized boundaries to produce sweeping, global decision surfaces with higher bias and lower variance. The sigmoid kernel computes the hyperbolic tangent of alpha times x transpose z plus c. Under specific parameter settings, the sigmoid kernel allows an SVM to mimic the behavior of a two-layer feed-forward neural network. Beyond classification, support vector machines can be adapted to regression tasks through support vector regression, or SVR. Support vector regression modifies the optimization objective by introducing an epsilon-insensitive loss function, forming an epsilon tube around the true target values. Any prediction error that falls within a margin distance epsilon of the actual target value incurs exactly zero loss penalty. The model ignores minor fluctuations inside the epsilon tube. Only prediction errors that fall outside the epsilon tube incur linear penalties scaled by slack variables. SVR finds a smooth function that keeps as many training observations as possible within its epsilon tube while minimizing parameter weight norm. Unlike logistic regression, support vector machines generate uncalibrated scalar distance outputs representing sign distance from the decision hyperplane rather than true probabilities. To produce probability estimates for downstream risk engines, staff engineers apply Platt scaling. Platt scaling fits a secondary single-variable logistic regression model on the raw distance outputs of the fitted SVM, mapping uncalibrated margin distances into well-calibrated probabilities between 0 and 1. Despite their mathematical beauty, support vector machines impose significant computational complexity and production scalability constraints. Training a support vector machine requires solving a dual quadratic programming problem across an n-by-n kernel matrix. Standard QP solvers take operational time proportional to n squared or n cubed. When dataset size n exceeds 100,000 observations, storing the n-by-n kernel matrix exhausts RAM capacity, and computing dual parameters requires trillions of floating-point operations. To scale nonlinear kernel methods to massive datasets containing millions of rows, staff engineers use random Fourier features, abbreviated as RFF or Nystrom approximations. Random Fourier features map input features into a low-dimensional explicit randomized feature space that approximates the Gaussian RBF kernel inner product. Linear models trained via SGD on random Fourier feature scale in linear time proportional to n, allowing engineers to retain nonlinear kernel modeling capabilities on massive data streams. Furthermore, inference latency in standard nonlinear SVMs depends directly on the number of support vectors retained during training. To generate a prediction for a single query instance using an RBF kernel, the model must compute kernel dot products between the query point and every single retained support vector. If a noisy dataset retains tens of thousands of support vectors, evaluating a single real-time API request requires computing tens of thousands of exponential kernel functions, introducing severe CPU latency. To mitigate inference bottlenecks in production, staff engineers apply support vector pruning, distill trained SVMs into fast decision trees, or transition to linear models optimized via gradient descent when sample sizes grow massive. In conclusion, support vector machines represent a masterpiece of geometric machine learning. By constructing maximal margin hyperplanes, introducing slack variables C and class weights to control variance, leveraging the dual formulation and Lagrange multipliers, applying the kernel trick via RBF functions with gamma tuning to operate implicitly in high-dimensional spaces, generating calibrated probabilities via Platt scaling, scaling to large datasets via random Fourier features, and adapting to SVR with epsilon tubes, software engineers can design powerful, mathematically rigorous classification and regression engines. In our journey through classical classification, we have analyzed geometric algorithms like support vector machines that construct maximal margin hyperplanes, optimization algorithms like logistic regression that fit continuous log odds functions, and non-parametric algorithms like decision trees and random forests that partition feature space into recursive conditional splits. The naive Bayes classifier introduces a completely different, highly elegant paradigm grounded directly in fundamental probability theory. At its core, naive Bayes approaches classification by evaluating conditional probabilities using Bayes' theorem. Rather than estimating direct functional boundaries between classes, naive Bayes constructs a generative probabilistic model that calculates the exact posterior probability that an observation belongs to a specific class, given its observed feature values. To understand the mathematical mechanics of naive Bayes, begin with Bayes' theorem. For a target class label y taking a value k, and an observed feature vector x containing p predictor variables, Bayes' theorem states that the posterior probability of class k given features x equals the likelihood of features x given class k, multiplied by the prior probability of class k, divided by the marginal evidence of features x. Each of the four probabilistic components in Bayes' theorem plays a distinct role in classification. The first component is the prior probability, denoted as p of y equals k. The prior probability represents our baseline probabilistic belief about the likelihood of class k before observing any feature data. In a training dataset containing 1,000 observations where 200 belong to class k, the prior probability p of y equals k is simply 20%. The second component is the likelihood, denoted as p of x given y equals k. The likelihood quantifies the joint probability that an observation belonging to class k would exhibit the exact combination of feature values observed in vector x. The third component is the evidence or marginal likelihood, denoted as p of x. The evidence represents the total overall probability of observing feature vector x across all possible classes. It acts as a normalizing constant, ensuring that the calculated posterior probabilities across all k classes sum to exactly 1. The fourth component is the posterior probability, denoted as p of y equals k given x. The posterior probability is the final output we seek to calculate. The updated probability that the observation belongs to class k after incorporating the observed feature evidence. During classification, we apply the maximum a posteriori decision rule, universally abbreviated as MAP. The MAP rule assigns an observation to whichever class k achieves the highest posterior probability. Because the evidence denominator p of x is identical for all candidate classes when evaluating a specific observation, we can omit the denominator completely during decision-making. The MAP decision rule simplifies to selecting the class k that maximizes the product of the class prior probability and the feature likelihood. To contrast decision frameworks, compare maximum a posteriori estimation with maximum likelihood estimation. Maximum likelihood estimation selects parameters that maximize feature likelihood alone, assuming all class priors are uniformly equal. Maximum a posteriori estimation explicitly incorporates class prior probabilities, making MAP superior when operating on imbalanced datasets where baseline class frequencies differ significantly. However, calculating the exact joint likelihood p of feature vector x given class k directly from training data introduces a severe mathematical wall known as the curse of dimensionality. To understand why calculating exact joint likelihood fails in high dimensions, suppose we have 20 binary features. A feature vector containing 20 binary variables has over 1 million unique possible feature combinations. To estimate the joint probability of a specific 20 feature combination for class k, our training dataset would need to contain multiple observations for every single one of those 1 million feature combinations. In high-dimensional spaces with continuous features, the vast majority of feature combinations will contain 0 training observations, making direct joint likelihood estimation completely impossible. The naive Bayes classifier resolves this high-dimensional estimation bottleneck by making a fundamental mathematical assertion, the naive conditional independence assumption. The naive conditional independence assumption asserts that all p predictor features in vector x are mutually conditionally independent of one another, given the class label y. This conditional independence assumption is described as naive because in real-world data, input features are rarely strictly independent. For instance, in a medical diagnostic system, symptoms like fever and high white blood cell count are strongly correlated. In text processing, words like database and query appear together frequently. Yet, naive Bayes explicitly assumes that once you know the true class label K, knowing the value of feature 1 provides zero additional information about the value of feature 2. Under the naive conditional independence assumption, the complex joint likelihood P of feature vector X given class K simplifies dramatically. By conditional independence, the joint probability of observing features x1 through xp together given class K equals the simple product of their individual single-variable conditional probabilities from feature 1 to feature p. This factorization transforms the calculation of joint likelihood from an intractable high-dimensional joint density estimation problem into a sequence of p-simple, single-variable probability lookups. The map decision rule for naive Bayes calculates the predicted class by finding the class K that maximizes the prior probability of class K multiplied by the product of individual feature conditional probabilities from feature 1 to feature P. Staff engineers select from 3 specialized variants of naive Bayes depending on the physical nature of input features: Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. Gaussian naive Bayes is designed for continuous numeric features, such as latency measurements, physical dimensions, or financial quantities. Because continuous variables cannot be represented as simple discrete frequency counts, Gaussian naive Bayes assumes that the continuous values for feature j within class K follow a one-dimensional Gaussian or normal distribution. During model training, Gaussian naive Bayes computes 2 simple sample statistics for each feature j within each class K: the sample mean mu sub kj and the sample variance sigma squared sub kj. During inference, the algorithm evaluates the conditional probability of a continuous feature value x sub j by plugging x sub j into the standard one-dimensional Gaussian probability density function using the class-specific mean and variance. Computing Gaussian naive Bayes parameters takes blazingly fast operational time. Estimating class means and variances requires a single linear pass through the training dataset, taking time proportional to sample size n times feature count p, with a memory footprint consisting of a tiny table storing 2 times p parameters per class. Multinomial naive Bayes is engineered for discrete count data, making it the workhorse algorithm for text classification, document categorization, and spam filtering. In text classification, a document is represented as a bag of words vector, where each feature j represents the term frequency count of how many times a specific word appears in the document. Multinomial naive Bayes models feature vectors using a multinomial probability distribution. The conditional probability of feature j given class K is estimated as the total number of times word j appears across all training documents belonging to class K, divided by the total number of all words appearing across all training documents of class K. To enhance text classification performance, staff engineers often combine multinomial naive Bayes with term frequency inverse document frequency, universally known as TF-IDF feature scaling. Raw word counts can be dominated by common words that appear frequently across all documents. TF-IDF scaling multiplies raw term frequency by the inverse document frequency of each word, downweighting ubiquitous words while boosting rare, highly discriminative keywords before feeding counts into multinomial naive Bayes. Bernoulli naive Bayes is tailored for binary Boolean features, where each feature j takes a value of 1 if a feature is present and 0 if it is absent, such as whether a specific security permission flag is enabled or disabled. Bernoulli naive Bayes calculates class conditional probabilities using a Bernoulli likelihood distribution, evaluating both the probability of feature presence when x sub j is 1 and the probability of feature absence when x sub j is 0. However, All variants of naive Bayes suffer from a critical operational vulnerability known as the zero-frequency problem. To understand the zero-frequency problem, consider a multinomial naive Bayes spam filter trained on thousands of email messages. Suppose a fresh incoming email contains a rare technical word, such as microbenchmark, that never happened to appear in any spam training message, but appeared occasionally in legitimate emails. When the model calculates the joint likelihood of the email belonging to the spam class, the class conditional probability for the word microbenchmark given the spam class evaluates to exactly 0 divided by total spam words, yielding a conditional probability of 0. Because naive Bayes multiplies all individual feature probabilities together to compute joint likelihood, multiplying by a single zero term causes the entire joint likelihood product for the spam class to collapse instantly to 0. The model concludes with 100% certainty that the incoming email cannot possibly be spam, completely overriding all other strong spam indicators in the message, such as suspicious links or phishing text. A single unseen feature value erases all other evidence. To eliminate the zero-frequency problem, staff engineers apply Laplace smoothing, also known as additive smoothing. Laplace smoothing prevents zero probabilities by adding a small positive smoothing scalar, alpha, to the numerator of every conditional probability estimation, while adding alpha multiplied by the total number of distinct feature categories k to the denominator. Setting alpha to 1 represents classic Laplace smoothing, while setting alpha to a fraction between 0 and 1 represents Lidstone smoothing. From a Bayesian statistical viewpoint, Laplace smoothing is mathematically equivalent to placing a symmetric Dirichlet prior distribution over the feature multinomial parameters. The smoothing hyperparameter alpha represents the pseudo-counts of the Dirichlet prior belief. By adding alpha to the numerator, an unseen feature receives a tiny, non-zero baseline probability rather than 0. This small pseudo-count ensures that an unseen feature slightly reduces the class likelihood without wiping out the product, allowing all other observed feature evidence to contribute to the final map decision rule. Calculating naive Bayes predictions across long feature vectors introduces a computational hardware constraint, floating point underflow. When multiplying dozens or hundreds of small probabilities together, each a fraction between 0 and 1, the running product contracts exponentially towards 0. In 64-bit computer registers, multiplying 50 small probabilities quickly exceeds floating point precision limits, causing the register to underflow to 0 and corrupting prediction outputs. To prevent floating point underflow, staff engineers compute naive Bayes using log probabilities. Taking the natural logarithm of the map decision rule converts the product of probabilities into a sum of log probabilities. The log map rule predicts class K by maximizing the natural log of class prior probability, plus the sum of natural logs of individual feature conditional probabilities from feature 1 to feature P. Because log probabilities are negative real numbers that add together linearly, log space calculations eliminate floating point underflow completely while converting slow multiplication hardware operations into blazingly fast addition operations. Despite the fact that the naive conditional independence assumption is almost always violated in real-world data, naive Bayes performs surprisingly well in practical engineering applications. Staff engineers analyze this apparent paradox through the distinction between probability calibration and classification accuracy. Even when input features are strongly correlated, violating independence, the joint likelihood product calculated by naive Bayes pushes predicted probabilities toward extreme values of 0 or 1, severely degrading probability calibration. However, for binary classification, The model does not need accurate probability calibration to make correct class assignments. It only needs the rank ordering of calculated class scores to remain correct across the decision threshold. Theoretical research demonstrates that naive Bayes produces optimal decision boundaries even under strong feature dependencies, provided the dependencies are distributed evenly across classes. Nevertheless, staff engineers must manage clear failure modes where naive Bayes degrades severely. The primary failure mode occurs when a dataset contains severe multivariable feature redundancy. If a feature pipeline includes 10 nearly identical correlated features, such as 10 redundant telemetry metrics tracking CPU load, naive Bayes will treat each redundant feature as independent evidence, multiplying its conditional probability 10 times. This double counting inflates the impact of redundant features, overpowering uncorrelated predictors and distorting decision boundaries. In production engineering, naive Bayes remains an exceptional choice for high-dimensional text processing, real-time spam filtering, real-time document tagging, TF-IDF keyword classification, and low-resource embedded deployment. Its ability to train in a single linear pass, update counts incrementally on streaming data feeds without full retraining, execute log space inference in submicrosecond latency, and run within minimal memory allocations makes it an indispensable tool in the software engineer's toolkit. In conclusion, the naive Bayes classifier represents a masterclass in probabilistic machine learning. By applying Bayes' theorem, contrasting map with MLE, leveraging the naive conditional independence assumption to factor joint likelihoods, selecting Gaussian, multinomial, or Bernoulli distributions, incorporating TF-IDF feature weights, preventing zero-frequency collapse via Laplace smoothing with Dirichlet priors, executing underflow-free inference in log space, and managing feature redundancy, software engineers can construct blazingly fast, highly efficient probabilistic classification systems. We have traversed the complete landscape of classical regression and classification machine learning algorithms. We explored the analytical mechanics of ordinary least squares linear regression, the partial coefficient interpretations of multiple regression, nonlinear basis expansions and splines, the bias variance trade-off governed by ridge, lasso, and elastic net regularization, the logit probability mapping of logistic regression, the comprehensive diagnostic metrics of confusion matrices and ROC curves, the non-parametric binary splits and cost complexity pruning of decision trees, the variance, decorrelating power of random forests, the geometric margin optimization and kernel trick of support vector machines, and the probabilistic foundations of naive Bayes. To synthesize these distinct paradigms into a unified engineering mental model, we begin this final chapter with a comprehensive comparative analysis. We will evaluate how each classical algorithm behaves across critical operational dimensions, establishing an explicit decision framework for staff engineers. Following our comparative synthesis, we will walk step by step through the architectural design, implementation, evaluation, deployment, and monitoring of a complete production-grade classification project. To select the optimal predictive algorithm for a specific production workload, staff engineers evaluate candidate models across 7 core architectural dimensions: decision boundary geometry, parameter interpretability, training computational complexity, inference latency, memory footprint, robustness to noise and outliers, and feature scale sensitivity. The first dimension is decision boundary geometry. Linear and logistic regression, alongside linear support vector machines, construct flat hyperplanes that divide feature space into linear half-spaces. When the true data-generating boundary is smooth and linear, these linear models achieve optimal generalization with minimal variance. Decision trees construct axis-aligned, hyperrectangular step boundaries, creating staircase approximations of nonlinear shapes. Nonlinear support vector machines using RBF kernels form smooth, complex boundary manifolds around data clusters in infinite dimensional spaces. Random forests smooth out the orthogonal steps of individual trees into flexible, nonlinear prediction surfaces that adapt to arbitrary shapes. Naive Bayes constructs smooth quadratic or linear boundaries dictated by class-conditional density distributions, though feature correlations can push these boundaries into distorted, nonlinear shapes. The second dimension is parameter interpretability. Linear and logistic regression offer clear structural transparency. Partial regression coefficients and odds ratios quantify the exact independent impact of each feature, provided multicollinearity is managed. Decision trees export transparent, human-readable nested if-else rule hierarchies that can be audited directly by non-technical domain experts or regulatory bodies. Conversely, random forests and RBF support vector machines operate as nonlinear black boxes, sacrificing direct coefficient transparency to achieve superior predictive accuracy. Naive Bayes retains moderate interpretability, allowing engineers to inspect class prior tables and single variable feature conditional probabilities. The third dimension is training computational complexity. Naive Bayes trains with blazingly fast linear time complexity, requiring a single pass through the dataset taking time proportional to sample size n times feature count p. Linear and logistic regression solved via stochastic gradient descent also scale in linear time proportional to n times p, making them highly scalable for massive streaming data feeds. Ordinary least squares computed via direct normal equations takes time proportional to n times p squared plus p cubed, becoming slow when feature count p is large. Decision trees take training time proportional to p times n log n due to continuous feature sorting operations. Random forests scale this cost linearly across B trees, taking time proportional to b times p times n log n, though training is embarrassingly parallel across CPU cores. Nonlinear support vector machines solved via dual quadratic programming scale poorly, taking operational time between n squared and n cubed, making standard SVMs computationally intractable for datasets exceeding 100,000 rows. The fourth dimension is inference latency. Linear regression, logistic regression, and naive Bayes deliver submicrosecond real-time inference latency. Generating a prediction requires computing a simple vector dot product between p weights and p input features. Decision trees execute fast inference by traversing array-based threshold checks down a depth-constrained tree. Random forests increase inference latency linearly by a factor of b, requiring query points to traverse hundreds of independent trees. Nonlinear RBF support vector machines exhibit inference latency that depends directly on the number of retained support vectors, requiring the computation of thousands of exponential kernel functions per query point, which can violate tight real-time SLA bounds. The fifth dimension is memory footprint. Linear and logistic regression require a tiny memory footprint, storing only a compact vector of p floating point weight parameters. Naive Bayes stores a small lookup table of class priors and feature means and variances. Decision trees require moderate memory to store node split rules and child pointers. Random forests demand a substantial memory footprint, requiring gigabytes of RAM to store node structures for hundreds of deep decision trees. Nonlinear SVMs require storing the feature vectors of all support vectors, consuming significant memory when support vector counts grow large. The sixth dimension is robustness to noise, outliers, and missing data. Decision trees and random forests are completely robust to feature scale and extreme outliers because their split decisions rely strictly on rank ordering rather than numerical magnitude. Furthermore, decision trees handle missing values natively using surrogate splits. Linear and logistic regression are highly sensitive to leverage outliers, which swing parameter estimates dramatically and require explicit feature imputation before fitting. Support vector machines are robust against non-support vector outliers due to their margin-focused loss functions, but remain sensitive to feature scale. Naive Bayes is vulnerable to correlated feature redundancy, which double counts evidence, but handles missing features effortlessly by omitting missing term probabilities from the log map sum. The seventh dimension is feature scale sensitivity. Linear and logistic regression alongside support vector machines strictly require feature standardization, such as z-score scaling, to prevent features with large physical units from dominating optimization loss surfaces or regularization penalties. Decision trees, random forests, and extra trees are completely invariant to monotonic feature scaling, producing identical split hierarchies whether features are in raw units, standard scaled, or logarithmically transformed. Using this comparative framework, staff engineers apply a principled selection taxonomy. Choose linear or logistic regression for high-dimensional, linear, or ultra-low latency APIs. Choose regularized ridge, lasso, or elastic net when feature dimensions p approach or exceed sample size n. Choose decision trees when audit transparency is mandatory. Choose random forests as the default robust non-parametric baseline for complex tabular data. Choose support vector machines for medium-sized datasets with complex nonlinear boundary manifolds, and choose naive Bayes for streaming text classification or low-resource embedded microcontrollers. Now, let us walk through a complete end-to-end production classification engineering project. We will follow an industrial machine learning system lifecycle across 8 systematic phases: problem formulation, exploratory data analysis, feature engineering, class imbalance remediation, hyperparameter optimization, model evaluation, production deployment, and operational monitoring. Phase 1: problem formulation and system architecture. Before writing code or processing data, staff engineers align model objectives with operational requirements. Suppose we are building a real-time transaction fraud classification engine for an e-commerce platform. The operational requirements dictate strict SLA performance boundaries. The inference engine must process incoming transaction payloads and return a fraud risk classification with an AP99 latency budget of 5 milliseconds, handling a peak throughput of 10,000 concurrent requests per second. The business objective is to minimize total financial loss caused by uncaught fraudulent transactions while keeping customer friction, false alarms that block legitimate checkouts, below 0.5%. This operational context establishes our metric hierarchy. We reject raw classification accuracy due to class imbalance, where fraud represents only 0.2% of transactions. We select area under the precision recall curve, PRAUC, as our primary offline optimization metric, and define an explicit cost-sensitive decision threshold based on the financial cost of uncaught fraud versus false customer block friction. Phase 2: exploratory data analysis and data sanitization. The raw transaction dataset arrives from distributed database logs containing 2 million rows and 80 raw attributes, including transaction amounts, device fingerprints, geographic locations, account ages, and historical velocity metrics. Engineers begin by inspecting missing data mechanisms. Missing values are categorized into three statistical regimes. Missing completely at random, or MCAR, where missingness is independent of all variables. Missing at random, or MAR, where missingness depends systematically on observed features. And missing not at random, or MNAR, where missingness depends on the unobserved value itself. For features exhibiting MCAR or MAR missingness, we apply median imputation for continuous variables and mode imputation for categorical variables, creating binary missingness indicator columns to preserve the signal that a value was missing. For continuous features exhibiting extreme right-skewed distributions, such as transaction amount, we apply logarithmic transformations to stabilize feature variance and reduce the leverage of extreme tail values. Engineers inspect feature correlation matrices and calculate variance inflation factors to identify severe multicollinearity. Redundant features with VIF values exceeding 10, such as multiple telemetry signals tracking duplicate time intervals, are flagged for consolidation or elimination. Phase 3, Feature Engineering and Feature Selection. Raw attributes rarely contain optimal predictive signals in their original formats. Staff engineers construct domain-specific engineered features to expose subtle operational dynamics. We construct historical velocity features, such as the number of transactions attempted by a specific device fingerprint within the past 5 minutes, 1 hour, and 24 hours. We construct interaction features, such as taking the ratio of the current transaction amount to the user's historical average transaction amount. For spatial variables like IP address geographic coordinates, we generate natural cubic splines to capture nonlinear regional risk boundaries. To encode high cardinality categorical variables, such as merchant category codes with hundreds of unique levels, we avoid creating hundreds of sparse dummy columns that would trigger the dummy variable trap or explode matrix dimensions. Instead, we apply target encoding with Laplace smoothing. Target encoding replaces each categorical level with the empirical mean of the target variable for that level, incorporating Laplace smoothing to shrink small sample category means toward the global target mean. Next, we run automated feature selection using Lasso L1 regularization and permutation feature importance. Features that contribute 0 permutation importance or whose lasso coefficients shrink to 0 are pruned from the feature pipeline, compressing the design matrix from 80 raw variables down to 35 high-impact features. Phase 4, Class Imbalance Remediation. Because true fraud represents only 0.2% of the training set, fitting standard classifiers directly on raw data causes models to overfit toward predicting the majority legitimate class. Engineers implement a two-pronged class imbalance remediation strategy combining algorithmic cost weighting and synthetic resampling. First, we set algorithmic class weights within candidate estimators, such as setting class_weight to balanced in logistic regression or random forest balanced class weighting scales the loss penalty of each class inversely proportional to its sample frequency, forcing optimization algorithms to penalize minority fraud errors heavily. Second, we apply synthetic oversampling using the synthetic minority oversampling technique, universally known as SMOTE. SMOTE avoids simple random oversampling, which duplicates existing minority rows and causes overfitting, by generating synthetic minority instances along feature space line segments connecting existing minority class nearest neighbors. To prevent synthetic points from straying into majority class clusters, we combine SMOTE with Tomek links undersampling, identifying and removing border pairs of opposite classes to create clean, well-separated class boundaries. Phase 5, Hyperparameter Optimization and Cross-Validation Integrity. To evaluate candidate models objectively without data leakage, engineers establish a rigorous cross-validation scheme. Because financial transaction data exhibits strong temporal ordering, applying standard random k-fold cross-validation creates catastrophic temporal data leakage. Training a model on future transactions to predict past transactions inflates validation metrics artificially. To preserve temporal integrity, engineers deploy a purged group time series split. The dataset is partitioned chronologically into sequential temporal folds. Between each training fold and validation fold, we insert an explicit purge window, a buffer period equal to the maximum feature aggregation lookback window, preventing feature values engineered from validation events from leaking into the training set. Within this time series cross-validation framework, we tune candidate model hyperparameters using Bayesian optimization. Unlike random search or exhaustive grid search, Bayesian optimization treats hyperparameter selection as a sequential optimization problem. It builds a probabilistic surrogate model, typically a Gaussian process, of the validation score as a function of hyperparameters, and uses an acquisition function like expected improvement to sample hyperparameter conditions that balance exploring uncertain regions with exploiting known high-performing configurations. Phase 6. Model evaluation and selection trade-off matrix. We train and tune 4 candidate model architectures on the training pipeline: regularized logistic regression with elastic net, a Gaussian naive Bayes baseline, an RBF support vector machine equipped with random Fourier features, and a random forest ensemble. We evaluate all 4 candidate models on the held-out temporal validation set across key operational criteria. The Gaussian naive Bayes baseline trains in milliseconds and achieves a blazingly fast inference latency of 0.1 milliseconds per request. However, due to feature dependencies among velocity metrics, its PRAUC score is low, evaluating at 0.42 with poor probability calibration. The RBF support vector machine with random Fourier features achieves strong predictive rank ordering with an ROCAUC of 0.91, but its PRAUC reaches only 0.61. Inference latency averages 2.5 milliseconds per request, consuming significant memory to store Fourier projection matrices. The regularized logistic regression model with elastic net penalty achieves exceptional interpretability. Its standardized beta weights reveal that historical device transaction velocity and log transaction amount ratio are the top linear drivers of fraud risk. It delivers submicrosecond inference latency at 0.05 milliseconds per request, and achieves a PRAUC of 0.68 with excellent Platt-scaled probability calibration. The random forest ensemble, consisting of 200 decision trees constrained to a maximum depth of 12, achieves the highest predictive performance across all metrics: a PRAUC of 0.84, an ROCAUC of 0.96, and an F0.5 score of 0.81. Inference latency evaluates at 1.8 milliseconds per request, falling comfortably within our 5 millisecond SLA budget, with a manageable RAM footprint of 450 megabytes. Balancing predictive quality against SLA constraints, staff engineers select the random forest ensemble as the primary production engine, while deploying the regularized logistic regression model as a lightweight, ultrafast fallback model in the inference service gateway. Using our cost matrix formulation, where an uncaught fraudulent transaction costs an average of $200 in chargeback fees, and a false customer block costs $10 in customer service friction, we calculate the optimal financial decision threshold for the random forest model. Sweeping across validation thresholds reveals that setting the decision probability threshold to 0.082 minimizes total expected financial loss, catching 94% of true fraud while keeping false customer friction at 0.38%. Phase 7. Production deployment and runtime optimization. To deploy the trained random forest model into low-latency production microservices, we do not export heavy Python serialization binaries that rely on slow dynamic runtime interpreters. Instead, staff engineers compile the trained random forest model into native C code or optimized C++ bytecode using compilation frameworks like Treelight or ONNX runtime. Compiling decision trees flattens nested node pointer structures into contiguous memory arrays, generating vectorized CPU instructions that execute the entire 200-tree ensemble in under 0.8 milliseconds per request. The compiled model is embedded into a high-performance Rust or Go microservice API container, deployed across auto-scaling Kubernetes clusters behind a load balancer, and connected to a real-time feature store that computes online velocity features from low-latency memory caches. Phase 8. Model monitoring, governance, and drift detection. Deployment is not the end of the machine learning lifecycle. Once a model is active in production, real-world data distributions continuously evolve, triggering performance degradation known as model drift. Staff engineers establish a comprehensive production monitoring suite tracking two distinct drift mechanisms: data drift and concept drift. Data drift, also known as covariate shift, occurs when the statistical distribution of input features shifts over time while the underlying relationship to the target remains constant. For instance, during a holiday shopping event, average transaction amounts and request velocities jump significantly compared to historical baselines. To detect data drift automatically without waiting for ground truth fraud labels, engineers compute the Population Stability Index, or PSI, and run two-sample Kolmogorov-Smirnov tests, or Wasserstein distance calculations comparing daily production feature distributions against baseline training distributions. The Population Stability Index is calculated by partitioning a feature's distribution into decile bins and summing across all bins the difference between actual production percentage and expected baseline percentage, multiplied by the natural logarithm of actual percentage divided by expected percentage. A PSI value below 0.1 indicates stable data distributions. A PSI between 0.1 and 0.25 signals moderate drift requiring monitoring. A PSI value exceeding 0.25 signals severe data drift, triggering automated alerts that notify engineers to inspect incoming data pipelines. Wasserstein distance, also known as the Earth mover's distance, quantifies the minimum work required to transform one continuous probability distribution into another. Unlike simple statistical tests, Wasserstein distance measures true physical distributional distance, making it ideal for monitoring continuous telemetry signals. Concept drift occurs when the true relationship between input features and the target label changes, such as fraud syndicates developing novel, unseen attack vectors that bypass historical rules. To detect concept drift, the system continuously ingests ground truth chargeback labels as they settle over weekly business cycles, tracking rolling PRAUC and Breyer score calibration metrics. When concept drift or data drift breaches established operational thresholds, the deployment pipeline executes an automated retraining trigger. The pipeline ingests recent sliding window data, runs smote rebalancing, retunes hyperparameters via Bayesian optimization, and evaluates the newly trained model against the active production model in a shadow deployment environment. In a shadow deployment, live production traffic is duplicated asynchronously. The active model processes real transactions and returns decisions, while the candidate model evaluates the exact same traffic in the background without affecting production outputs. If the candidate model demonstrates superior PRAUC and lower expected financial cost across a 7-day shadow evaluation window, the system executes an automated canary deployment, routing 5% of live traffic to the new model and ramping up to 100% after verifying 0 runtime errors. Finally, staff engineers implement model interpretability and governance tools for audit compliance. For every transaction flagged as fraudulent, the API generates local explanation vectors using SHAP, which stands for Shapley Additive Explanations. Derived from cooperative game theory, SHAP values calculate the exact additive contribution of each input feature to the final prediction score relative to the baseline average prediction. The SHAP value for a feature represents its marginal contribution averaged across all possible feature subset coalitions. If an account is blocked, the API returns the top 3 SHAP feature attributions, such as high device velocity, unrecognized geographic region, and high amount ratio, providing complete transparency for customer support agents, security auditors, and regulatory compliance teams. In summary, building production-grade classification systems requires mastering every stage of the machine learning engineering lifecycle. By conducting rigorous comparative analysis to select optimal model architectures, sanitizing data, engineering discriminative features, mitigating class imbalance via SMOT and cost weighting, enforcing time series cross-validation integrity, optimizing hyperparameters via Bayesian search, compiling models for sub-millisecond runtime inference, monitoring data and concept drift via PSI and Wasserstein distance, executing automated shadow deployments, and providing local SHAP interpretability, software engineers can construct world-class, highly resilient machine learning systems. Congratulations on completing this comprehensive masterclass. You have developed a deep staff engineer mental model covering the core mathematical foundations, geometric trade-offs, and practical design principles of classical regression and classification algorithms. Armed with these insights and real-world engineering strategies, you are now fully equipped to build, evaluate, and deploy high-performance predictive systems in production environments.